All right, so I guess over the last year, there have been a bunch of typing proposals floating around in sort of GitHub conversations or the typing email sig. So what I wanted to do is just take a few of those examples, ones that are sort of popping up more than others, discuss some of the changes that are going on to Python type syntax, and then really open the floor for a discussion. So this talk will probably be more discussion based than some of the other ones we'll see today. If I haven't met you yet, I think quite a few faces look familiar, but I'm Maggie. I work on the Pyre team at Facebook, and I've been there for about 2 years. So nice to virtually meet all of you. So yeah, once again, we're going to have lots of time for discussion. So I'm going to run through a few examples or a few proposals fairly quickly. Don't stress about writing down the examples or anything. I'm going to bring them back later when we talk about it, so you will have that as a reference. Yeah, and I'm just curious, there are a few frustrating points of types in Python that we get as the Pyre team, people asking us questions of being like, hey, this is kind of verbose or really clunky. So I'm curious for other people, if in your own Python projects, are you experiencing the same things that we're seeing? Or do you think that these proposals will solve any of the issues that you are seeing in your projects? So first, we're going to talk about the union syntax. There is a PEP out for optional syntax. There are quite a few proposals that are floating around for new syntax for callables. And then there are a few for typing various types of collections. So we'll start with the union syntax. This has been added to CPython and it'll be released in Python 3.10, and it's outlined in PEP 604, if you're wanted to go read that after this. And basically it just replaces the import from typing using the square brackets with the pipe operator. So one thing that I find doesn't look great with Python types is that you can end up with all of these nested square brackets, and this, I think, makes it look a lot cleaner. So this is just an example of how much shorter a function signature can be using the new union syntax. And we've actually patched a version of Python at Facebook. So we've added this feature to one of our projects, and we've gotten a really good response so far. So we've actually had someone code mod away all of the old union syntax. So we're actually only using the new union syntax in one of our projects, and it seems pretty popular so far. The added benefit of this is that it does give us another way to express an optional type. So just like you can express an optional type with the old union, you can do the same thing with the new one. This brings us to new syntax for the optional type as well. So the current proposal is to have a postfix question mark as an optional type. And we see this in languages, Hack, Flow, TypeScript. So other gradually typed languages do use a question mark to denote some type of optional. Swift and C, I think, have something similar. So it's syntax that's familiar to most developers. Would be fairly easy to teach and easy to pick up. If I saw this and I hadn't come across any documentation for what that question mark does, I probably have a pretty good intuitive idea that it's something that's optional. So there were other proposals for this. There was the tilde. This had the added benefit that it would be a little bit easier to implement because we wouldn't have to change the parser or anything for Python. And there was a prefix operator with the question mark as well. But the current proposal is postfix question mark. So this is what it looks like currently. So you have to import from optional and then use those square brackets. So if you have a function that takes in a few optional types, it's pretty long. If we replace this with the new union syntax, it does clean it up quite a bit. But if you add in the new optional, it makes that function signature a lot cleaner. There was some discussion of like, hey, how is this new optional syntax going to play with the new union syntax? I think the convention should be to have the question mark on the last element in that union list. I think it looks better. I think it's easier to see at a glance, oh, this whole thing can be an optional. But also just because it looks odd if you have it in the middle. So I don't think I've ever really seen any example of a union where the none is in the middle. And I don't know if I'm alone in just thinking that it looks strange, but curious to see what other people think of that. Okay, so callables are a thing that pops up quite often, being like, this is confusing, this is verbose. So this example is fairly straightforward. You have 3 arguments and 1 return type, fairly easy to glance at and understand. But if maybe the return type is an optional, and the return type of our callable is awaitable, and one of them is a union, and another is a list, and another is a dictionary, you end up with so many square brackets that it's really hard if you are editing this type and you delete one to then figure out where it's supposed to go. And you end up with error messages that look like this, and you're trying to spot the difference between the two. And this is a fairly tame example. The Pyre team does get questions sometimes where someone will be like, hey, what does this error message mean? And it's just like a block of a type. So I think there is some room for improvement here. And there are quite a few proposals. So I'll just give you guys a second to sort of look at them, think about maybe the pros and cons you might want to bring up in a few minutes. But most do sort of replace the outer typing.callable with an arrow of some sort. I think there are other syntax ones out there sort of floating around. Again, GitHub conversations, there's an email list, but these were the ones that popped up most frequently. Okay, so there is some changes. PEP 585 proposes that we enable support for generic syntax for all standard collections that are currently available in the typing module. There is a proposal to also include immutable types. There's no convenient way to specify immutable types the same way that there is with the other collections. People will follow the path of least resistance. You might end up with a lot of mutable types that should be immutable. So there's a proposal for this. And then this was a more recent one, but I did think it was interesting and maybe worth bringing up. I personally am not super fond of this one, but I'm curious to see what other people think. So it just proposes having special syntax for tuples or iterables. So again, I'll just give you a couple seconds to look at it. And then let's start with the discussion with optional syntax. I'm not going to discuss union syntax in too much detail just because it already is implemented and sort of coming. So yeah, Shannon, I'm not sure with a group this size, did we want to split into breakout rooms for a chat or see how people do with the giant grid?
Does everyone know how to raise your hand? Oh yeah. Okay, I see your hand.
Okay.
Okay. If you want to just call on people with their hand raised and just put your hand down if you're called, that could be a good way. Unless it gets too unwieldy, then yeah, we can use breakout room.
All right, David, you popped up first. Oh, I think you're still muted.
Here we go. So just wanted to contribute that you had a slide early on that had optional syntax, union syntax, and callable syntax. Of those three, the optional syntax is the one that I've been most wanting simplification for. I'm happy to see that the new union has the bars, and I like this. But I'm definitely looking for something specifically for optional. So that was just that was one of my comment here.
Okay. Is there a specific reason behind that, or just in general? Really
it's the one I use the most commonly. So I use a lot of optionals and a couple of unions and just a smattering of callables, but we use like optionals all the time.
Okay, great. Yeah, I think we use optionals quite frequently. Last time I checked. Yellow? I'm not sure how to pronounce your name, sorry. Okay.
Yeah. And for what it's worth, I like the postfix question mark. Anyway, I'll stop now.
Okay.
Yeah, I think optional has been confusing for a lot of users because people often think it means an optional function argument instead of something that can be none.
Mm-hmm.
I like that the or none syntax makes it explicit that it actually means or none instead of optional arguments. And for that reason, I don't like the question mark syntax because I think it might go back to the same confusion. In TypeScript, question mark means that you can actually omit an argument instead of letting it be no or undefined. And in Python, we're going to make it mean something different. It doesn't mean you can omit it. It means it can be none. So I'd actually prefer not to see the question mark syntax.
Do you think that like the tilde proposal was something that you were more excited about? Or do you think it would just be like an educational thing of telling people this is an optional?
I think I like just having the or none syntax. It's very explicit
Okay.
and tells people exactly what it means.
Okay. Guido, you are next.
Oh, Yella said everything I felt I wanted to say. So just a big +1 there.
Okay. Carl?
Yeah, I just wanted to expand slightly. You didn't go very deep into like the sequence and mapping the immutable types and why, like what some of the reasons are that it's valuable to not make it hard to use those relative to the mutable ones. And what we see a lot of is like one of the main points of confusion with type errors is the invariance of mutable containers. It takes people a long time to get their brains around that. And so if you can preemptively encourage people to use immutable types as much as possible, then they see less of those confusing errors. And so that's the reason why we would maybe not want to make the path of least resistance to be always using the mutable types.
Thank you. I agree. Sebastian.
Yeah, we started using the slash what's called pipe non syntax quite a bit in our code base, and it's definitely an improvement over using optional. And it works quite fine, I think. I think one of the problems I see with the question mark, especially if you have a quite long list of different types, like you have the int pipe string question mark, is that the question mark is fairly easy to miss, I think. I mean, and another idea that I have about the question mark when combined with the pipe syntax is to maybe just use parentheses around the union and put the question mark at the end. I'll just put it in chat what I mean. Yeah, that's it.
Okay. Lucas?
Hi. So when we were originally discussing like PEP 484, like I was proposing like this postfix like question mark thing since I saw it at Facebook, and at the time I remember like first of all the reaction was that, oh no, we will have to change the parser, so that's kind of out of the question. But even if it weren't, the story went that we don't really want to make it very easy to just mark everything as optional, because it's kind of, you know, it's sort of like static typing is partially to express what types we already have. So like partially it's about the state that the code is already in, but increasingly importantly, it's about designing something new when you're writing it, right? And when it's kind of just viscerally very easy to just make everything optional, then you will just do that. And just having to just type those few other characters, and like I don't remember if I had this conversation with Jukka now or Guido, but like that was what 6 or 7 years ago. Like, but well, the rationale was like just make people think about optionals because they are sort of viral, and then, you know, we can tell much less about the type that you have, because you have to have those non-checks everywhere.
Rebecca?
Oh, I had a question about the immutable collections proposal, because I just hadn't seen that before. As far as I know, sequence and mapping aren't currently names in built-ins. So is the idea that those would be added there so that you don't have to import them, or would they still be imported from some namespace?
I think the idea was hopefully they would be added there. Carl might have a little bit more context there. But I think, as far as I understand, if we're going to sort of make those as easy to use as possible, it might make sense that you don't have to import them.
Okay, thank you.
Zoom has stopped showing me people's names, which is
Oh, I can
It only shows
yeah, I
you the
can
name
call
of the
people.
person talking. Okay, that'd be great because I can't see
Yeah.
people's names.
No problem. I think Jake, your hand's up.
So in relation to the first two things, we've been showing the pipe syntax since before the PEP was accepted in Pyrite and Pylance. And we found that to be a massive improvement. But also in the case of optional, we don't show optional anymore. We show something pipe none. So my inclination is that it's pretty likely that the or none is like the most obvious thing to do rather than a postfix or a prefix thing. But that's just from my experience of, you know, trying to show what things are at the moment. And when we're collapsing things down, we'll go, oh, there's an optional in here, and then split it back out again. So we've done this for a pretty long time.
Do you want, up to you. I'm not sure if I should.
Yeah, go ahead.
Okay, Jukka?
This is sort of a meta observation, but it is like whenever new syntax has been proposed, like in Python ideas, there's a lot of resistance from the community. So the bar for adding new syntax, even though that new Pyre makes it kind of easier to do it, I think still it's kind of an uphill kind of battle sometimes. So I think one thing you might need to make compromises, because then right now then that would the new syntax would probably be usable in all expression contexts, so that you can use it in like base classes and casts and such. So then you could imagine that some other parts of the community study like kind of abusing the type syntax from like our point of view. Well, obviously they don't consider it as abuse, and use it for non-type sort of use cases. So I'm just being like, there's kind of that aspect. I don't have a good solution for that. I've been proposing. I think about, could we make type syntax kind of distinct from like expression syntax? And I have some thoughts about it, but I haven't written a full proposal. But I think that's something, if we do that, then it would be much easier likely to add new syntax, because then you couldn't use it everywhere. So you could have an own kind of part of that syntax, like where we can kind of more freely add more stuff.
Adrian?
I quickly wanted to mention the PEP 505, which was deferred 3 years ago, and it would also use the question mark syntax, but for a distinct but similar purpose for null safe calls, like for example in Kotlin. Just wanted to mention that quickly.
Yeah, when what is it, PEP 645 was written for the optional syntax, it did take that into consideration, that it would, if that PEP wanted to go forward, this optional syntax wouldn't block it.
Okay.
Carol?
Yeah, I'm somewhat the typing skeptic when it comes to reading code, just because I have found it really busy. Now, in terms of production code, it's quite nice. And I think, Maggie, you're on the right track here. I think in terms of readability, I think the bar none is nicer than the question mark. The question mark as a writer of code would probably be nice because it's less, but with type completion, I think it's maybe less important. But I do think, you know, as I look at younger engineers who are newer to Python, typing is sort of a visual barrier for them to understand the code base. And anything that you can do, like the new union, is a huge improvement. So thank you for that.
It's interesting. I think we often make the argument that types make it easier for new engineers. So it's interesting to hear that perspective.
It makes it easier for the documentation aspect of coding. I will give you that. But in terms of the readability and the ability to quick scan, I've long been needling Brett to have VS Code turn off typing at least in the display, so that when I'm reviewing code, it's a lot quicker. But that's me.
Guido?
Couple things. I think that personally, and based on some statistics that I've seen, the most important next thing to try to improve is callable syntax. The current callable syntax is the least readable of all the sort of special kinds of syntax we still have. And the callable keyword occurs more in a typical typed code base than anything else in my experience. I also had if I may, I also had a follow-up on Jukka's idea of doing more sort of special syntax for typing. I don't know if you're aware, but there was a major kerfuffle a few weeks before 3.10 beta 1 was released, where we had to reverse Lucas's from future import annotation becoming the default PEP 653. Because what happened is actually that a whole group of new packages have come up that started using annotations at runtime that are very dependent on sort of annotations being expressions. And so I don't know how much freedom we will have in the future to make the annotation syntax different from the expression syntax, given that sort of this major event happened very recently. And that's all I have to say about that.
Rebecca?
Before we move on to callable syntax, I had a follow-up question for Jake about his comment that Pyrite/Pylance are already using a pipe to show union. And that seems like a really appealing thing to do, because in my experience, users struggle a lot with verbose error messages and trying to figure out what they mean. But I was curious if there's any problem with people being confused by the type checker showing syntax that they then can't actually use themselves in their code.
So we haven't had any sort of feedback that said that they didn't like it in that sense. And if users do try to use it, we detect that their Python environment is of a version too low to support the feature. And then we basically tell them, hey, if you want to use this, you can up your Python version to be Python 3.10, either, use an interpreter, but in our case, we allow you to configure and say you can have 3.10, right? That's how we test all these extra features. So we haven't really gotten that sort of feedback. It's just been a visual improvement to sort of eliminate all those different things. So we did that about a year ago, in fact. So we enable that for everybody. And I think that, so there are other sort of choices that can be made about sort of decluttering this syntax. So for example, we already show callables in proposal 2. And I think we have for a pretty long time before Pylance was a thing in our tooltips. And then another thing is that I believe there was an error message that was shown on one of the slides that was like, this pipe is incompatible with this type. And it just shows those two types. I can't remember which slide that was on, but, oh, there it is. Yep, that one. Where when we're displaying errors in Pyre and Pylance, we drill down and say, all right, this lines up with this type, this lines up with this type. So you can clearly see that the mismatch is actually here. So I believe that the TypeScript compiler also does the same thing. But in this case, there's a difference in the types here. It says incompatible type where it expected one thing. And we would show like the differences in this part of the type versus showing a single line error message that says this is incompatible and we're not going to tell you why. So that sort of makes things a little bit easier to determine when it comes to comparing these complicated types. But obviously, I look at this and I go, oh dear. But we already show this in a different format anyway.
Thank you for the detailed answer.
I tried to paste the screenshot, but Zoom didn't let me do that. So I'm too used to Teams, I guess.
Well, oh yeah, 5-minute warning on the discussion. I see a bunch of new hands. One thing that we also have available is a poll. So I know that we have like a couple options listed for callables, and I'm not, if Maggie, you wanted to grab some opinions, I can make you a poll. Just a heads up. But Lukash, I think your hand is up. I'll make one in case it's easy to use.
Great, thanks.
Yeah, just wanted to quickly add that like another thing that Visual Studio lets you do is when you are using the now controversial future import, it will stop like, you know, being annoyed at you using the new syntax because it's all strings anyway. So I've been using them for like, I guess, over a year now. And you know, whenever I make a talk and I actually use those, like, you know, people like them a lot. And I just found like seriously like no issues with that. Yes, you cannot use the new syntax in old Pythons in the runtime you know, scenarios, but most of the time, like, you know, it's just function signatures. Speaking of callable syntax, one proposal that is not there that, you know, like I was always sort of like intuitively coming to is that if you define a class A, right? You have a class A, it has some contents, and then you can use the name A as your type in places. I always wished we could do the same for callables. Like, you have a callable, you can even make it in this sort of syntax like stubs where I just specify types, ... but it already has a name. Like, if I could just use that somewhere, like, that would be amazing, because it literally tells you what I expect. I don't see it as one of the proposed syntaxes for it, but like, for me, it would be much less magical than all of those sort of, well, excuse the expression, artificial syntaxes for a function signature, because we already have a syntax for a function signature, so why not use it?
Stephen, I think you're next.
Yeah, I think this is related. I'm relatively new to thinking about typing in Python, but as a user of Python, I have frequently found it challenging to navigate that not all the function signatures that I want are expressible with the callable signature, in particular, like quargs and things like that. Proposal 3 looks like it partially addresses that, but that's something that I would want to think about ideally, is just how to capture as many of the signatures as we're likely to want in the syntax.
Pradeep?
Sorry for interrupting, but since it's only 2 minutes left for the presentation of David, what I would encourage is for continuing the question for people to move to the room A, and like probably Maggie, you can join there and people can continue asking questions, so that, you know, we keep the timing and David can start on the.
Do I go forward?
Yeah, I think we have time if you want to finish. Yeah.
I think one sort of feature that the current callable syntax doesn't have is the ability to specify the parameter names. So you can't say that I want it to have, say, parameter foo, or you can't say star args must have this type, or star quargs must have this type. If we have syntax, we could mimic the sort of function signature that we have so that it looks more natural. So yeah, that's one sort of thing to keep in mind for callable syntax.
Okay, great. So David, I think you are presenting next. If you want to start setting up your screen share. And yeah, if Maggie, if you're willing to, if anyone else has questions about this or wants to just like, I don't know, record an opinion or something, you could use the breakout room A, just sort of opt yourself in. And yeah, I guess worth noting that the chat I actually think was quite nice during discussion. So if people are not seeing this, make sure to click on the chat tab and maybe pop it out even. Could be a good way to comment on whoever's talking if you don't want to raise your hand yourself. All right, David, all yours.
Cool. So can you hear me and see slides?
Yes.
Okay, cool. All right, well, I'll get started. So I'm David Foster. I'm CTO at TechSmart, where we're inspiring the next generation of K through 12 students and teachers to code and generally create neat stuff with computers. I'm also the original implementer of TypedDict in MyPy. So today I wanted to talk with you all about JSON and specifically how you can use Python's typing system to format and parse JSON that conforms to a well-known protocol or a schema. It's very common for JSON to be used in web applications. So on this slide, I have an example of a web API that, given a particular year, will list out some number of movies that were made in that year. Each movie here is expressed as a dictionary in a particular format with a particular set of keys mapped to a set of values. So titles are strings, years are integers. We can express this in Python's typing system explicitly using something called a TypedDict. It's available directly from the typing module in Python 3.8, and it's available from typing extensions in earlier versions. So the idea with TypedDict is it's pretty much a drop-in replacement for dict, except that it also tells type checkers that it expects a particular set of named keys mapped to certain values. So if you declare a TypedDict here with the class-based syntax, you can have a movie that's from that JSON blob, which has the title and year. You tell it in code that it is a movie type, and then the type checker will let you know if you made a mistake. So let's actually go into writing like an actual web API for formatting JSON. So here's a really simple endpoint using bottle that if you hit this endpoint, it will return you a single movie as a JSON structure. And just for starting out, this is not using any special typing facilities. It's just using a plain dict. So here I'm just directly returning a single movie just as a plain dictionary. So this works and it's fine. However, if you make a mistake, you add extra keys, you misspell a key, you have the wrong type, there's no ability for a type checker to know if you made a mistake because it doesn't know anything more than it's just a plain dict. So, and even worse if you like change the protocol. So movies don't just have a title and year, you add like who are the stars in the movie. If you change the protocol and you have existing code that's trying to conform to it, you won't get any warning if there's an inconsistency. So if you instead, you take that definition of a typed dict of a movie and you drop it in where you were previously using a plain dict, then a type checker will be able to tell you if you made any mistakes of that kind. So this is a little bit on formatting JSON. It's worth noting that a typed dict can be dropped in anywhere that code would normally expect a regular dict because TypedDict actually erases to dict at runtime. So if you actually take this expression movie of title year and you ask it at runtime what type of object it is, it won't say movie, it'll say that it's a dict. So if you take anything that's declared as a type dict and you pass it to a function that expects a regular dict, it will just work. In particular, JSON dumps, which serializes JSON. It will work with that. So everything I've talked about so far is formatting JSON. What about parsing? This is much more troublesome if you don't have some automation around it. So the hard way of parsing JSON is you just literally check to see whether it's a dict, whether it has the correct keys, whether the keys have the correct types. And in this case, if it does all those checks at runtime, then it uses the cast operator to tell a type checker that's like, hey, we assert that this is definitely in the format of a movie now. So this can be done. but it's super verbose. And we're only, it's already pretty verbose, and we only have 2 keys. If you have a definition of a more realistic JSON blob, which has nested dictionaries and things with optionals and discriminated unions and a whole bunch of other things, then it can get to be much, much messier. So you might think that you can replace all that code with something like this, where you just use isInstance, which you normally can use, be like, does this value map to this particular type? And that works for most things. But if you actually try that using a TypedDict type, you'll find that it doesn't work. So TypedDict, along with a couple other styles of type annotations, describe more the structure of a value. I guess you might call them structural typing rather than a nominal type. So isInstance only can check things that are present at runtime. TypedDict erases to dict, so it can't check that. And in fact, there are many things that isInstance cannot check that are common in JSON. So can't check type dictionaries, it can't check typed collections, so list event, set event, etc. And another thing that's very common in JSON is you may have unions. So you may have a, say, like a shape type, which could be one of a couple different types of dictionaries. It could be a square dictionary, it could be a circle dictionary, and those dictionaries are told apart by a special key, usually called type. So you'd say type string square or type string circle, and you would use that type key to distinguish between 2 different elements of a union. This is sometimes called a discriminated union. So that's relatively common in JSON. So isInstance can't deal with any of this stuff. And it's all very common in JSON. So I was like, okay, well, I want to write this. I want to write something like this. How can I do that? So that brings me into introducing a module that I wrote called trycast that helps you do this type of thing. Trycast provides 2 functions. The first one is called isAssignable, which is pretty much a drop-in replacement for isInstance, but it can also check these types of structural types. So it can work with TypedDict, it can work with union of something pipe something, can work with any of the things that I listed before. And so it's really nice for checking to see whether, in particular, a JSON blob conforms to a protocol that is defined in terms of typing annotations. Trycast, the module, also provides trycast, the function, which is kind of like cast, except that it actually does a runtime check to see whether a value is assignable to a particular type or a type annotation. And if it is assignable to that type, then it returns the original value casted to that type. If it does not conform to the structure, then it returns a none, which is to say that trycast here can replace the entire parse movie function. Because if you say trycast to a movie this value, that has exactly the same operation as our parse movie function. So with these 2 new functions from the trycast module, let's take a look at rewriting our parse function. So if we have parse movie, before I had isInstance, I can just drop in isAssignable, and that works. That's cool. But I can make it even shorter. So trycast does the entire functionality pretty much of parse movie. So I can trycast to a movie of a value, and then that will return the value casted to movie if it matches, and none if it doesn't. So since parse movie is entirely done by trycast, I can just straight up inline that into a web API. So here's a variation of the web API endpoint that I did before. This one, instead of formatting a JSON and returning it to the browser, it takes a movie in from the browser and parses it to Python. And here, that goes, the value from the browser is request.json, and then I'm just directly parsing that using the trycast function here. So that's pretty cool. But there's just one thing that's a little bit weird. We've got this extra cast around trycast. So that's not ideal. What can we get rid of that? So the reason that there has to be an extra cast around a trycast call is the signature for trycast isn't able to express in Python's current typing system that the runtime type annotation value that you're passing to it as the first argument is related to its return type. In particular, we want to have something like, if you say trycast to a movie, that it's going to return an optional of a movie. So we've got an association between the runtime type annotation value and the statically determined return type for the function. So I want to somehow express two type checkers that these two values in the signature are the same, but I can't. So it's like, what can we do about that? Well, here's where something new called TypeForm comes in. TypeForm is a proposal for a new type annotation syntax or type annotation form, which can describe any type of type annotation object at runtime. So that would be anything that you can currently assign to a type of T, so any kind of class-based type, but it also includes other types of type annotation objects. So it includes the unions, it includes TypedDicts, includes anything that you can write as a type annotation object and then use that at runtime. Similar to type T, using variables. So here we have a type form of T, and then we have trycast returning an optional of T, which is to say that the particular value passed in as the first argument for trycast is associated with the return type here. So yeah, if you have this kind of syntax type form, then you can go back to that web API endpoint, and now you no longer need a cast because a type checker now can say, okay, trycast movie, let's look at the signature. Oh, that means that the return type is optional of movie. So then I don't actually need to do the extra cast at the end explicitly to optional movie because it just has derived that. So that is trycast and typeform. Trycast is available as a PyPI module right now, and it can already parse pretty much all the interesting things that you would find in a JSON object. So that's available right now. You still need to use that extra cast around it because typeform is not yet a thing. But typeform is something that I'm looking at making into a PEP at some point. So we may have the ability to use typeform and then get really, really succinct parsing using that additional syntax. So that's all I've got in terms of presentation. I think I've been given 10 minutes for just general discussions on this. So happy to hear your questions. Okay. All right, I see a question from Matthew.
Thanks for that. Super good talk, David. With the first of those, trycast, is it hard-coded? Does it try to deal with structural types in some sort of generic way, or does it sort of hard-code the list of structural types it supports?
It understands, so it's able to so it introspects the object that you pass it at runtime. So let me see. So if you say trycast movie, what it does is it actually takes the movie type at runtime. It sees that it's a typed dict. It can ask that object, what are the required keys? What are the optional keys? What are the types associated with that? So yeah, it introspects the object and then figures out how to detect the structure by introspection. It supports many typing features, but not all of them. So it does support typed dict. It supports union. It supports several typed collections like list and set, but there are a couple other collections that it does not yet support. And there are things like protocols, which it does not yet support, which it could support. So there's actually there's a roadmap on the project page for like, I would like to add support for checking all these other types of types.
Gotcha, thanks.
Jake?
I guess I have a dumb question, but what is it about type that makes it such that you can't already use it? I guess I'm surprised that you need a new construct coming from having used type in other circumstances or how type works in other languages.
Yes, so you used to be able to use type of t to represent a number of things, but at least in the MyPy type checker, there was a change that was made such that if you had an annotation like union of something to something, that was not interpreted as a type T, but is interpreted instead as an object. I forget precisely the reason why that was done, but the effect of that is I would like to use type T here and do the association, but that actually isn't possible. And it looks like it was intentionally restricted to have certain type annotations reduced to object type rather than reduced to type of T. So it's a partial answer, perhaps. Jukka. You are muted.
Sorry. So about the MyPy behavior. Yeah, so right now MyPy treats only supports like classes, a single class as or any within type, or maybe a union of class. I'm not even sure about it. It's going to be changing a lot. So the question is like, what does PEP44 say about it? Does anybody remember? Could we extend type to support anything else? Because then I can see some problems with that. Then potentially with things like this instance, but
yes,
which currently accepts type objects, but you can't give it like arbitrary type.
I just did this in Pyre, and it works exactly as you're expecting it to without Typeform. If you just throw type of T on there, I can have type trycast union of intstr, pass in a value, and I get back out optional of intstr. So I don't know exactly where the restriction lies necessarily if we're already implementing that.
Yeah, I think, before adding Typeform, I think it would be worth investigating, like whether there's could we just extend type T?
Yes.
I wonder whether like older typing versions will
the original
problems with that.
Before I started designing Typeform, I'd originally proposed making type T work the same way as what I've just specified here, which is to say broadening, like officially broadening its scope to include things that are not necessarily supported with isInstance, but there seemed to be some pushback. But yeah, definitely open. Yeah, I also think that like reusing type T rather than introducing something new might be a good way to go if that was acceptable.
Ethan?
Yeah, I actually just looked at PEP 484, and it does say specifically that for type T needs to be a class. So you'd need to either modify the PEP or have a new one probably to update it to extend that, I think. So I definitely think that would be a cleaner approach, though, in many ways.
Jukka?
I don't know how you want to deal with this, but I just want to point out that there's a question in chat from Avanindra.
Let me see if I can bring that up. Here we go. Let's see. Pydantic, a question about Pydantic. Let's see, so yes, so I'm aware of Pydantic. The main difference between the approach that I'm using right here is that it's just using the existing type annotation syntax. It's not requiring you to define a new class type that your structures need to conform to. So like I already have a lot of data that's going back and forth already as JSON objects. And so it was convenient to not have to convert it into a new type of class before I would do other types of checks. So that's on Pydantic. Let's see, Pyrite. Okay, cool.
Jake?
Sorry, I forgot to put it down. My bad.
Ethan?
I also forgot to put it
Okay,
down.
I wasn't sure. Cool.
Sorry.
Oh, I think there's another question in chat, actually.
I see it. So I'll read the question. Has there been any serious investigation into being able to generate TypedDict objects based on JSON schema, JSON-schema schemas? Beyond the current scope here, no doubt, but I'm curious if TypedDict is powerful enough to accurately reflect all of the constructs available in JSON schema. So I'm not actually familiar with JSON schema myself, so I'm not sure. Yeah, I'm not sure. I expect that trycast or something like it could be extended so long as there's enough information at runtime available for type annotation objects in order to introspect the properties. For most type annotations, this is possible, but for some, it's more difficult. This doesn't apply for JSON, but for example, something that's annotated with callable, so callable taking certain parameter types and taking a return type, it's not possible given like a callable object at runtime to know, at least I don't think in general, it's possible to know what types it's expecting for the arguments and what types it's trying to return. So if you tried to do like trycast with a callable, which was filled out with specific parameter types and a return type, there doesn't really seem a way that it can actually check that, which is to say that trycast could be upgraded insofar as you can discover the related information at runtime.
Okay, I think we can leave the presentation here and continue questions probably in room B. And yeah, it's time for Pradeep. Pradeep, are you ready?
Can everybody see my screen?
Yeah, looks good.
All right, I think I'll wait for a few seconds. And just want to check whether we mentioned the recursive aliases for the previous one. Yeah, like we might want to formalize that. Sure.
I think Eric brought it up in chat, but we didn't really talk about it. Yeah.
Yeah. All right, let's get started. Hi, everybody. I want to discuss type variables and what they might look like in the future. So I'm Pradeep. I've been working on Pyre, which is Facebook's type checker for Python. I've been working there for 1.5 years now. So we've all heard of the Zen of Python. If you type import this in a REPL, you can see the guiding principles of Python's design. The key among them are the principles of simplicity, readability, and obviousness. So the Python type system usually does a good job of being simple and intuitive, while still being quite expressive. We have callable types, we have protocols, we have quite a lot of cool features. However, based on my own experience when writing type Python and that of users who ask questions when they get stuck, there is one area where I feel the type system is still pretty complex, not very readable, and at times not at all obvious, namely type variables. So in this talk, I'll go over a couple of areas where I found users have a hard time getting the Python type system to do what they want. So one is self-type, the other is the syntax itself. I'll propose some tentative solutions for these situations, and then we'll start a discussion where you can share problems you come across and we can debate pros and cons of different solutions. So here's a typical problem I've come across. You have a class, say shape, and you have a method that returns self. So you want to say that this method returns an instance of the current class. So this is usually called the fluent programming style, where you can sort of chain different methods one after the other. So the way you would do it is basically say the return type is shape with, and when you use it like this, and you try to call shape.setScale, you can see that the return type is inferred to be shape. So far, so good. But what happens if you create a subclass circle, which has some method, say setRadius? Now, if you try to create a circle and then say setScale on that, the type is inferred as still shape. And now when you try to say chain a setRadius on top of that, you end up getting an error saying shape has no attribute setRadius, right? So the problem was the return type of setScale was too general. When it's a shape class, we wanted to return shape. When it's a circle instance, then we wanted to return a circle. So now most of us have sort of encountered this problem at some point and figured out the workaround either by reading the docs or trial and error. So we have to import typevar. We have to define, say, a type variable t-shape with the bound as shape, and use that as a type for self, and then use that as a return type. So if you do all these, then when you try to call circle.setScale, the return type will be bound correctly as circle, and then you won't have any error. So clearly this works, and we can teach this to new users every time they come across this situation. Another sort of very similar problem is you have a class method. So say, again, you have a shape, and you want a class method that constructs a shape from a given dictionary, say like a dictionary of which contains the scale value. So now when you try to create a shape from a configuration, the type checker infers it to be of type shape, which is fine. But if you have a subclass like circle and you try to create that from a configuration, the type is again too general. It's seen as type shape. And when you try to call a circle method on it, you end up getting an error, right? So once again, the workaround is quite tedious. You have to define a type variable. You have to define, and you have to say that class has type t-shape, and then the return type is t-shape, and so on. If you do all these correctly, you will get the expected behavior for such class methods, right? So both of these problems do have solutions, but they're quite unintuitive. So the first time I needed to do this, I was stuck. I had never seen a type annotation on self or class parameter. It didn't even strike me that they could have annotations, right? So even after reading some docs, I was unsure if these would work as expected. Secondly, it's quite a bit of special setup needed. We saw that we had to use type of t-shape and stuff like that. And it's error prone because if you miss any of these, say, bounds, or if you forget one of these steps, you would get confusing type errors. So how frequently does this pattern actually show up though? Like, this might be fine if it's a rare edge case that only sort of core typing modules have to deal with. So I found that 1/4 of all type variables are sort of used for annotating self or class. So this was true in Typeshed. It was also true in other projects that I looked at. Sort of another fact is that like when I looked at class methods, about a quarter of them used a type var to specify what the class parameters type should be. And many of the remaining class methods were often either unsafely using the base class as a return type, like shape, or they just omitted the return type, which sort of defeats the purpose of typing. So given how confusing it can be for programmers who just want to write everyday code, it's worth making this easier to use. So how do other languages sort of approach this problem? There's no clear sort of equivalent of self or class in other languages, but there is a pattern of expecting a parameter to have the same type as the current class. So for example, if you have a TypeScript class shape, and you want to say same as, you want to have a method same as which expects an other, and then just compares those two. So TypeScript allows you to say that it must be of type this, which is to say like it must have the same type as the current class. Now, if you have a subclass like circle, and you try to compare a circle with a shape, you will get a type error, so which is what we want. So let's try something like that in Python. So if you have the method returning self, we could ideally just specify that, hey, I want to return self. So we can express that as a special keyword self. And the type checker would treat this code as if we had returned the code on the left, which says the long tedious version where you say self is a type var, and then you sort of annotate the self parameter and the return type. The same goes for a circle set radius. You're returning self, so just make the return type be self, which would be equivalent to as if you had sort of created a self variable for circle and then used that in its methods. Likewise, for the class method, where we sort of constructed from a configuration, we would again just say that it returns type self. We don't have to create a type variable as on the left. You don't have to sort of annotate class parameter as type of self. And finally, if you want to use a parameter that is expected to be of the same class as this one, you can say other must be self, which would be equivalent to the code on the left. Same if you want to apply a callable, you can just say callable self none without having to like go around as you do on the left. So overall, I think this leads to a simple heuristic. If your function is returning self, you can just make the return type self. You don't have to annotate self or class or do anything else. I find it more readable. We get to express our intentions without the syntax sort of getting in our way. Otherwise, if you want to understand some code, you have to sort of go back to the definition of the type var to see what the exact bound is, just to get a good mental model of what's happening. Here is just self. Finally, this seems harder to mess up. Users will be less likely to just sort of omit return annotations or use any, just because it's too hard to use the right solution. And if we sort of implement this, this would make a quarter of all type variables easier to implement, easier to read. Some sort of disadvantages here are that there are now two ways of representing a self type. One is the sort of the type var way of doing it, and the other is using self. I believe we could deprecate support for the old version where we had to do the sort of explicit support. And there may be a name clash. So I think that's something else we have to consider. So I want to take a couple of minutes here to discuss this before moving on to the next topic. So are there any questions, comments?
There's some mention in the chat, which is interesting.
Oh. Written type. Oh yeah, we don't do implicit things like that, but I think that's interesting. Got it. I think I can't see names here.
Oh, Ethan.
Can you just point out Shannon?
Yeah, Ethan.
Ethan, hey.
Yeah, so it sounds like a really great proposal. I love using self-types in languages like Rust. And I think something like that in Python would be good. I'm a little concerned about how we would introduce the name into the scope, since it sounds like the runtime semantics of types will need to stay in Python at least for another version, or maybe more. So is this something that you see being imported from typing,
Yeah, that is one option, I think.
Okay.
I was also wondering if it's possible to just make it a special keyword, but like you said, that could lead to problems.
Right.
So yeah, I'm open to either.
And then the other follow-up I had was, you said that you wanted to deprecate the other way of defining self-types. Could you explain why you want to deprecate that?
Deprecate in the sense, because now we would have two ways of representing the same thing, right? So yeah, maybe we could just allow it anyway, but yeah, I was wondering what to tell people when they say, hey, which of these do I use? I think we can just say, just use self always. I think Yella is saying we could make typing.self be a singleton like any.
Jake?
Yeah, I don't know how much you're reading chat, but I think that a couple of type checkers automatically have this behavior whenever you have an unannotated self or class. Do you think that it'd be worthwhile to maybe standardize this behavior so that implicitly it does the right thing without people having to annotate it, and then maybe introducing this syntax as a simplification rather than having it be like the only way to achieve this behavior?
So just to clarify, are you saying that we don't have so what would be the difference?
So I don't know if you had read Eric's comment on this, but in our case, whenever we detect that a self is unannotated and you're trying to use it from, say, like a child class, and you're calling a parent class, something like that, we go, oh, that actually was unannotated. So whenever I analyze this function, I really need to refer to it. It's like it creates the type var automatically for you, so that if you're doing something with self and I return self, it knows that actually it's a type var bounded by the current class, and then the user doesn't actually have to do anything. But if the type is actually annotated, then we do what it says. But in the default case, what people normally write in unannotated code that we're just analyzing off the hook, then we just have this behavior already, right? So if this were the sort of quote unquote standard behavior where self is automatically assumed to be type var bounded by the current class, then you obtain this behavior without having to introduce any new syntax. But I do agree that the type var stuff is kind of gross and would be worth simplifying, and throwing something into typing seems reasonable.
Got it.
As like a marker.
Yeah. So you're saying if the code is unannotated, then we can use the implicit behavior that you mentioned.
So specifically self or class, right?
Yeah,
so those special positional arguments.
Yeah. I think Lukasz has a question.
Oh, so that's actually a question about the Pyrite behavior. So if this is the case, that it automatically kind of assumes the return value of self, then what does it do if that function just omits the return value but is actually none because there is nothing? Or what does it do when the value is self but the user forgot one of the paths and one of the paths ends up being none? Or what if actually that returning none is well, deliberate and it should be optional self? So like what happens in those cases?
I'm not sure what you mean exactly. Like if a function, if let's say we have a function that's in the base class that has an unannotated self, and it can either return that self variable or none, then the type that we infer for the return type, if it's completely unannotated, is the type var that we constructed out of thin air for that self or none. So it's already a union. If you want to explicitly type it, then there isn't a way to achieve this behavior, and you do need the type var, right? So for having everything completely typed out, then there is a reason to have this.
Yeah, I mean, my misunderstanding was that like how do you actually infer it, right? So like is it only when you actually see that in all cases the returns from that particular method are already using self?
Yeah, that's correct. Yeah, return type inference is based on all of the return statements in the function.
I see. Okay, makes sense.
All of the return type expressions.
Oh, so then you become more of an inferencer than a checker, right? Because in this case, you cannot really show people errors because you just assume that whatever is the case is true. So what I mean is like with Pradeep's proposal, if there's a return value of self, but you actually don't do it, like the type checker can tell you, hey, like you forgot to actually return. But in your case, like you like that's the actual difference, right? Like you just infer what happened and just treat it as deliberate.
Just sort of to interrupt, can we sort of continue the discussion at the end? I want to sort of go into the next topic and then we can sort of catch up at the end. Thanks. So yeah, I think this situation sort of came about because self and class were parameters that were pretty much unique to Python. So let's look at another sort of type system feature that is not found anywhere else, which is the syntax itself. So if we want to make a class generic in Python, we have to import generic type var, define a global variable t, and then use that as a generic base class generic of t. So like practically all other languages, like say Java, TypeScript, Scala, allow you to bind a type variable like right when you want to use it. So you can just say class mylist with t and then use that within the scope of the class. So that means our current approach is largely unfamiliar to new users. It also makes code sort of hard to read, especially in large files where you sort of have to go to the definition of the type var, which is usually defined at the top, and see, double check whether the bound is what you think it is before you can continue reading the code. So I'm sure we've all come across type var abuses in the wild. So one example is somebody may try to define and use a type var just right where they want to use it. It makes some sort of sense, but yeah, it doesn't really work. There are many ways to sort of do this. I'm sure like you have your own experiences. Users may think that you have to use the exact type variable with which a class was defined. So if t-shape was defined in the shape module, you sort of go to the length of sort of importing exactly that type variable before you can use it, because they think that that's what you need to do. Or they may be confused about type errors, like say you define a type var t and you use it within a class, and they might say, why is this complaining about t not being in scope? It's right there in scope. And if they're like casual users, they might think the type checker is mistaken and they just add a type ignore and move on. So that happens quite often, right? So clearly it would be useful to design the syntax in such a way that these problems don't occur as often. And so people don't avoid using type variables just because it's hard. However, I have to mention that there is a significant constraint beyond the difficulty of gaining consensus among the typing community. So that's one thing. At this point, I think the Python Steering Council had recently commented something like this. At this point, we're reluctant to add general Python syntax that only benefits the static typing language. So this might be, this is a consideration we have to keep in mind. Even if we have sort of neat ideas for better type syntax, it may be challenging to add to the language itself. That leaves us with a sort of trade-off here. 10 years from now, we want to have syntax that sort of aligns with the principles of simplicity, obviousness, is sort of more familiar to new users, but we may not be able to add the most desirable syntax to the language. I still think it's useful to discuss this right now. We may be able to come up with better alternatives, implement some features incrementally, and then end up with great syntax 10 years down the line. So with that in mind, let me just propose one sort of view of how type variables may look, and then we can all sort of discuss constraints and different sort of alternatives. So I found that half of all type variables are used for generic functions. So currently a function like makePair needs to have an import, needs to have global definitions, and then you can use it just to create a tuple of two type variables. We might have syntax like this, which just says that, hey, I want to use t1 and t2 as type variables and then use them as needed. Likewise, if you wanted to use something which is bound to shape, right now you have to go through this, and you have to name the variable just to make it like super explicit what its bound is. That's what I found in the wild. You could just have inline syntax that said, hey, s extends shape, and then just use s as it is. So this would make reasoning about a function be more local. You can just focus on reading that code. You don't have to read what came earlier in the file. You can refactor it. You can move it to a different file without much trouble. And just for completeness, any string might look something like this. We can just say s is either string or bytes, and then you can use it as it is. So these are just placeholders for whatever syntax we might want to think about. And then a quarter of all type variables were used for typing generic classes. So this is the current state where you have to sort of go through all these steps. We might want to have something like this maybe, where the generic, just using generic t would bind T within the scope of that class. So this could be one sort of minimally intrusive change, which might make things easier. Another alternative would be just to use the sort of explicit syntax saying that container with T can be used so that we don't have to specify the generic base class. But this is a sort of more extensive syntax change. Subclasses might remain the same because I think we have to specify what the type variables are. So I don't see much of a change there. Variants, for example, right now we have to specify a type variable, and then with a flag like covariant is true. We might have something like just plus, which means, hey, this is covariant. And like for contravariant, we could just say that minus means contravariant. So this is used in languages like Hack, which use this syntax. And just quickly, paramspec was introduced recently for adding precise types to decorators. However, the sort of unfamiliar name and the import may be sort of intimidating for users writing everyday code. Maybe better syntax, like say **p, could make it much easier to use decorators so that people aren't tempted to just use callable ... any, which I find quite often. So this might help. So yeah, I believe such syntax would meet our requirements of being simple, readable, obvious, and would also be more familiar to users coming from other languages. The problem, of course, is that this requires syntax change, especially for generic functions. I think that is the sort of main hurdle I see. So one possible compromise could be that we implement the syntax incrementally. For example, the generic class syntax is requires minimal changes. So that might be something we want to go for first. And then we could consider generic function syntax later on, since that's sort of more radical. We might also want to consider what happens in the worst case scenario where no syntax change is possible for types as such. Maybe we could have some sort of workarounds that don't require syntax change. So this might mean something like T is bound within this function and T has an upper bound string. And we could sort of make it more succinct, but this wouldn't require syntax change. So yeah, just to sort of recap, I'm sure a lot of you have opinions and expertise on the area of syntax. I'm interested in hearing how you would approach this problem. Thank you.
Also worth flagging that there's thoughts in the chat already.
Oh.
People can't wait. But yeah, I can call on hands if anyone has.
I think Jake.
So I don't know how deeply you want to go into things that were in the chat. Some things that I think would be interesting is in relation to like that previous discussion about how, you know, we had to yank support for deferring annotations because people are using them as values. Some of the syntax, I would wonder how those kind of things will be used at runtime as well. Like I know that in the series slide, you had, for example, had annotated something bound by stir where it used operators and a bunch of stuff. And if those things need to be produced at runtime, I'd be curious how those things can be extracted out or represented in the same way. It's sort of like the same sort of problems as the new callable syntax would have, where if those things need to be representable at runtime, how are people supposed to, you know, how do we deal with that problem?
Got it. I think that's a general problem with syntax as a whole. I think Matthew is next.
On the subject of type variables in Python being difficult for new users, I'm wondering how much that's Python's way of doing it versus type variables just being kind of complicated in the first place. Do we have any data about how difficult sort of new users find type variables in other languages?
Yeah, I don't have data as such. I think this is mainly from comments that people say Python's type variables are particularly aggravating. So I haven't seen those kind of comments about other languages which have inbuilt syntax. So they say, hey, why is this so hard to use, or why is this so unintuitive? That's what I've seen, but I don't have like raw data as such.
Interesting. Yeah, I wonder if it might be worth reaching out to some folks who do type checking in other languages to get some more evidence about that. But yeah, thanks.
I think Guido is next. You're muted.
Okay, now I'm not muted. My main comment is that if you want syntax, I think at this point it's clear that it's important to discuss that on Python dev and not just on the typing sig. Because that's sort of the steering council is wary of the typing community going off in sort of into the deep and leaving the rest of the Python community behind, because they're honestly among the core developers and the steering council themselves, there are still a lot of typing skeptics or people who in their own use of Python just don't use typing much or only use it for certain applications. And they're not as convinced as the folks who hang out on the typing sig that types are good for everyone. And so it sort of, there's just the general risk that if we come up with a perfect solution, that we end up sort of getting rejected because we never had a discussion with the rest of the core developers, and the steering council watches that, but they don't watch the typing sig. So that's sort of a
Thanks. Follow up a little bit on what Guido just said. As a steering council member, I think what he's saying is spot on. For every strictly typing PEP that gets approved, whether it's for the best in typing, my personal view on typing is it's great in production. It's not necessarily ideal when you're teaching new Python developers. And for every time we accept a PEP that is typing specific, my email box gets full of the, oh my gosh, you're ruining Python because you're adding types, even though types is optional. But I think what we saw recently was that runtime, Pydantic is relatively new, but it's gotten really huge adoption in the last year and a half, and same with Fast API. And I think just having a broader discussion on Python dev as opposed to only typing sig, I don't want to give the impression that the steering council will never approve a typing only PEP. That doesn't seem reasonable, but and it is too constraining for all of you, but it's more like, that consensus building it needs to be broader than just typing today.
Got it. Thank you. Thank you for the context.
Thank you.
I want to follow up that a common question I get is from people who are teaching Python, and they just ask, should I start teaching type annotations now because type annotations are in the language? And of course, they're aware of other languages that always have types where they have to teach the types. I always say, teach the language without the annotations. It is a fine language as such. The annotations are for certain sort of large-scale software development enterprises much more than for beginners. So don't bother beginners with types, and that's a good message to repeat occasionally.
Yeah, and I also think the direction, like from the first talk that we had today about simplifying the readability of how we're doing typing today, that's exactly on the right path, because then the transition from no types to types becomes much smoother, just sort of like as you add any knowledge of any other feature in Python to a new user.
I think Yella had a question.
Yeah, I guess I had a comment. I think from an implementation perspective, the function syntax is probably a lot easier to get right than the class syntax. The base classes have to be evaluated at runtime, and to get around that would probably require pretty invasive changes, like generic might have to be treated specially in the core language. The function syntax would also require new syntax, but that actually seems simpler to do. So if you want to push this forward, I would recommend getting the function syntax first, because the class syntax would be more complicated to implement.
Yes.
Thank you. Ethan?
Sorry to interrupt, just saying that we are officially in the break time between sessions, so feel free to keep discussing. I will stop the recording. Yeah.
On the Instagram Python language and runtime team. And I'm going to talk about static Python, which is an experimental project that we've been working on that I'm pretty excited about. And I'm curious to find out what you all think of it. So I'm going to start, before I get into that, I want to do the what's become sort of a PyCon tradition and recognize that the land that I'm currently speaking to you from in the Black Hills in South Dakota is unceded treaty territory of the Ochatishakowee or Lakota Nation, which was illegally taken and settled by the United States. Okay, so I'll start off with a summary about what static Python is and how it works. I'll talk a little bit about semantic differences from normal Python, our motivations for working on it, and last, a little bit about our results with it so far. First, I want to recognize some projects that have been part of the inspiration for static Python. Python has been around for a long time and has its own type syntax that predates static typing in Python. So it compiles a Python-like language to C API code. MyPyC is a more recent project from the MyPy team that compiles well-typed Python to C extensions. And the JVM and .NET also were part of the inspiration for static Python. Both are managed language runtimes that support statically typed languages with bytecode that carries type metadata, which is linked at runtime. And lastly, we were also inspired by reading in the literature on sound gradual typing. This includes work on languages like reticulated Python, typed racket, among others. I've linked a few specific papers at the end of the talk. So what static Python aims to provide is performance similar to MyPyC or Python, but with a pure Python developer experience. So no extra syntax, no extra compilation steps, and seamless gradual adoption. We achieve this in RC Python fork with a custom bytecode compiler. The compiler first does a declarations visit of the AST, building up the type environment. This recursively visits imported static modules, so we get their types too. Then we bind types through the AST. This might find static type errors, which are treated as syntax errors and fail compilation. Then the fully typed AST goes to CodeGen. In CodeGen, we might emit some type specialized opcodes, which are new. Then the bytecode, of course, goes to the runtime, which also has added support for static Python. There's a class loader that's able to look up types by their import path, which is embedded in the bytecode. And it also constructs vtables and typed slots for static Python classes. And then, of course, the runtime also has support for the new type specialized opcodes that we might emit. Our runtime also has a method JIT that compiles Python functions to native code. This isn't required to run static Python, but it does get the best performance out of it. So design goals. We want static Python to be compatible with other type checkers and the typing PEPs. So you should be able to take well-typed Python and compile it with our compiler. And static Python source should still be Python source. It should compile and run correctly with or without the static compiler. The compiler should be an optional optimization. Static Python should still be dynamic and gradually typed Python. You don't have to annotate everything to use our compiler. And last but not least, static Python should be safe. So today in static typing in Python, it's accepted that your type annotations and stubs might be wrong, perhaps by accident, or perhaps intentionally to cover up some dynamic complexity that the type checker can't handle. And that's fine when the worst that will happen is you might get false positives or false negatives from a linter. But in our case, it's not fine. The worst case is that you get a seg fault. And so if we're relying on static types at runtime, we have to be very conservative about what types we trust. So what types can we trust in a function we're compiling? Some values will originate within our code as literal integers, strings, dictionaries, etc., or constructs like comprehensions that produce a fixed type. Clearly, we can use these types. And if we're compiling the whole module, we can also trust global constants from within the module as long as we deal with the patching problem, which I'll come back to later. Beyond this, all of our values come from outside, such as our arguments or the return value from a function that we call. And we can't trust anything from outside, no matter how it's annotated, since annotations can be lies. So all of these outside types, initially, we have to treat as dynamic, similar to the any type. So what we've got so far here basically is just constants. That's not going to be enough to optimize very much. To increase our type coverage, we'll need some runtime type checks or casts, which have some cost. So the game becomes, how can we do the minimum casts that get us as many trusted types as possible? So we'll start with one principle, which is that we want our annotations to be correct in the static Python code. So at function entry, we'll check argument types, and then we can trust them. And I lost stability. There we go. Yeah, minimize casts, maximize types. So yeah, we'll check our argument types at function entry, then we can trust those. If we have an annotated assignment and the right-hand side is dynamic, we can insert a cast there and trust that. And if we have return value, we want that annotation to be correct. So we want to ensure that we actually return an int. So if we return something dynamic, we'll insert a cast there as well. These last two casts on the assignment and the return are only inserted if the value is dynamically typed. So if we have a static type, if something here were statically known to be an int, we wouldn't need a runtime cast for either of those. If it were statically known to be something other than an int, then we would, of course, emit a type error in compilation and fail compilation. So we verify annotated arguments on function entry. We accept that there will be dynamically typed values within our static Python. We're okay with this, since we can always just emit normal dynamic Python bytecode for operations on them. But we will runtime cast those dynamic values anytime we assign them to a typed destination, which could include an annotated assignment or a return, or there are some other cases I'll get to. So the next step to minimizing our casts and maximizing our types is to take advantage of network effects. I said before that we don't trust anything from outside, but we do know that a static Python function guarantees its return type. This means that if we call such a function, we can trust the return type. We can also do better when passing arguments to a static function. So here we're passing an int to the callee, which takes an int. These are both static Python functions, so we know statically in the caller that we're passing an int. We don't want to waste time in the callee checking the argument types again. So we'll actually skip argument type checks anytime we make a static to static call. And it becomes the caller's responsibility to ensure that all the argument types are correct for those calls. So if we have a dynamic value in the caller for this argument, then the compiler has to add a cast here before it makes the call. So we avoid redundant casts by trusting return types from static callees and by trusting argument types from static callers. Our experience has been that this approach gives good type coverage at a manageable cost in runtime casts, with nice network effect improvements as more related code is made static. So let's look at an example of how this works quickly. Here's a small static module. We import a non-static function to get a scaling factor, and then our scale function just multiplies a given int by that factor. In the disassembly, static Python hasn't been able to do very much yet here. There's just two new opcodes. At the top, there's check args. If we're called with a non-int, this will throw a type error. So now we know for sure that val is an int, but we can't trust the return type of get scaling factor. And even if we could, val could be a subclass of int that overrides dunder mul to do something weird. So the value we're going to return, we also have to consider dynamic. But we have to actually return an int. So the compiler adds a cast opcode, which will throw a type error if the value we're about to return is not an int. In both of these new opcodes, we see something we'll see a lot of in static Python, these tuples that we call type descriptions or type deskers, which provide the runtime with an import path to the referenced type. Now let's make get scaling factor also a static function. Now we see another new opcode in the disassembly. Instead of load global and then call function, we have invoke function. Oops. We have invoke function. With a type desker tuple for the function to call. So this opcode invoke function tells us that we're making a static to static function call. So that will skip the initial check args in the called function. Let's take a deeper look quick at how this opcode works. If we're just naively executing bytecode in the eval loop, each time we hit invoke function, we have to go off and ask the class loader
to resolve this tuple to an actual function that we can call and then move on with the bytecode. This is fine and it works, but it's not fast. It's probably slower than the load global call function pair that we replaced. What we need is a one-time link step where we resolve these type references and store the resolution so we don't have to repeat it. There are actually two different execution tiers where we do this. There's a bytecode quickening tier and there's our JIT. I'm going to skip the quickening layer for now for time reasons and just talk about the JIT briefly. A JIT compiler is perfect for optimizing invoke function. JIT compilation of the function is our link step where we can look up the function to call and burn it into the generated code. So in production, the JIT will compile this invoke function down to a single x64 call instruction to a fixed address in most cases. Since the static compiler already knows the target signature and the provided arguments, in many cases, we can just put the arguments in the right x64 registers and emit this single call, which ends up having no more overhead than a C function call. You might be wondering reasonably about patching. What happens if someone patches the target function and we aren't calling what we expected to? So we bypass this problem partly by making all static Python modules and types immutable in production. We only allow patching through a specific API and only in tests. And the JIT can tell at compilation time whether or not the target function is in fact in an immutable container. If it is, it just emits the fastest possible path. If the container is not immutable because we're in tests, then we JIT compile with a thin layer of indirection so that we handle patching correctly while still being quite fast if nobody actually patched us. So for comparison, this is the GDB disassembly from an optimized CPython build for calling one Python function. And it's not even that this is wasteful. This code path is reasonably well optimized in CPython, but Python is a very dynamic language, and this is handling lots of dynamic cases that are important for Python semantics. So with a few small exceptions, our aim in static Python is never to remove that dynamism from the language. Our aim is to leverage static type information to rule out in advance the cases we don't need to handle so that we can safely, in the best case, reduce all of this to this. So our workload at Instagram is heavily object-oriented, like a lot of Python workloads, and a lot of the performance we get from static Python comes from improving attribute access and method calls. So the static compiler will scan this class and automatically add under slots so that attributes are laid out at fixed memory offsets instead of in a dictionary. It also adds a new slot types attribute that tells the runtime the type of each slot. In the runtime, we have a new typed descriptor that checks types on assignment so that we can be sure that a static instance's attributes will always hold the correct types and only the correct types. So the bytecode for the area method here shows a few new options. Load field loads an attribute from a slot. In the JIT, it will compile down to a single indexed load, which is again orders of magnitude faster than a normal dynamic load adder. There's also store field, which is correspondingly similarly just a store, a memory store. And these opcodes bypass the type descriptor. So the effect of that is that within static Python, where the compiler is providing type safety, we get very fast attribute loads and stores. But if a static instance travels into non-static code, then attributes set on it are type checked at runtime via the type descriptor. And then we also get a new invoke method opcode here, which uses vtables built by the class loader to do a fast lookup of the method to call. Okay, so that was getting kind of deep into the weeds, but here are most of the new opcodes that we add in static Python. We've already seen all the ones in the left column. The middle column here are all related to unboxed machine integers and floats, which is pretty important for static Python to be competitive with Python on numeric code, but it's a topic I don't have time to get into here. In the third column, there's some additional opcodes that we use for sequence types, for lists, and also for array and vector types that we've added. So fastlen is just a direct load of OB size from the C struct. Sequence get and sequence set are just indexed loads and stores from an offset into OB items. So you might be wondering how this is safe, since something annotated as a list might be a subclass of list with arbitrary dynamic behavior. For example, here we know that L is a list, but that doesn't mean we can bypass dunderlen and go straight to the OB size field, since a subclass of list could override dunderlen. So at runtime, what we'll do is we'll check if the object is an exact built-in list, and if not, we take a slower path. This is still very efficient in practice,
both because the type identity check is very fast and because 99% of the time in practice, if something is annotated as a list, it's probably going to be a real list, not a subclass. So we have to handle that case, but it's not common. In some cases, we can even know statically that it's not a subclass. For example, if it came from a list comprehension, we know it's definitely a built-in list. And in this case, we don't even need to omit the slow path. Okay, so we've covered the basics of what static Python does and how it does it. Let's summarize how a static Python module is visibly different in terms of Python semantics. The most obvious difference is that now you get runtime type checking kind of for free. If we define a function taking an integer and then call it with the wrong argument type, which we can only do from non-static code, because in static code, that would be a static type error and the code wouldn't compile. But if we call it from outside of static Python with the wrong argument type, we'll get a runtime type error. The other obvious one is the slotified classes. So you can no longer tack on ad hoc attributes to individual instances if they aren't part of the class layout. And then third is, as I mentioned earlier, we do make static Python modules and types immutable after construction, with an exception for patching and tests. So our feeling is that all three of these are very natural restrictions for statically typed Python. If you're violating any of these restrictions, you're probably already running into problems with your type checker. And in our experience adopting static Python, we haven't had trouble with any of these restrictions. The important thing is, beyond these, static Python is just normal Python. Anything we don't understand in the compiler, or if there are dynamic features being used that invalidate our optimizations, we just fall back to dynamic Python behavior and trade off some speed for dynamism. So in some sense, static Python is probably poor branding for this, because the aim is really that it's dynamic Python with some static optimizations. So what are our motivations? Why are we doing this? The most obvious reason is that we always want to be faster, and static Python is fast. So that's maybe our primary motivation. But there is maybe a second one, which I think is maybe most relevant for discussion in this group as far as sort of the future of statically typed Python, which is developer experience. So this is backed up by a 2018 study that did a study of various gradually typed languages and found that across the board, developers working in such languages preferred runtime type enforced semantics given a choice. And it also matches my experience talking with developers at Instagram who now have several years experience working in a fully typed code base. This quote, I think, gets at the heart of the preference. So without the runtime enforcement, there's this uncanny valley between the type checker's understanding of your program and what actually happens at runtime. Your static types may intentionally lie to cover up complexities, or may unintentionally be wrong, or some call sites might not be covered by the type checker, so incorrect types can sneak in anyway. We expect there will always be highly dynamic Python code that lives outside the type checker's understanding. So static Python allows and assumes this. But as we expand the part of our code base that is statically well typed, static Python eliminates the uncanny valley and offers assurance that our type annotations can be trusted. There's also quite a few packages on the package index attempting to provide a similar experience via decorators and dunder annotations. But of course, doing this in Python code has a large performance cost. So my feeling is that if we can provide these enforced semantics without a performance regression, that in and of itself would be a big win for type Python. If we can do it with performance improvements, that's like a bonus. So one more thing I should mention in terms of motivations. There's a reasonable question, why don't we just observe the types at runtime? If our motivation is to be faster, we could just profile types at runtime and then speculatively optimize based on those observed types instead of using static types at all. So that's a reasonable question. You could probably do a lot of similar optimizations that way. So part of the reason that we're using static types is because, as I just said, we think that compile time and runtime enforcement of static types is actually a win for the developer experience of using type Python. And also just we had the static types, and this was a faster way for us to get to some of the performance wins. That said, we do plan to also implement speculative optimization, and we think that the two approaches are complementary. Speculative optimizations always require a guard and a slow path. Statically known ones don't. Okay. So yeah, a little bit about our actual results with static Python so far. We are using it in production. It's easy to throw around benchmark numbers, like we can get up to an 8x performance improvement on a typed Richards benchmark with this. But translating benchmark wins to production wins can be pretty tricky. So what's our experience been in production? Our initial focus has been replacing our use of Python, and we've so far replaced around 20 Python modules in production, some of them quite heavily tuned Python. In every case so far, we've been able to replace the Python with static Python in the JIT with no performance regression. In a number of cases, performance has actually improved with the switch. We've won back about 0.7% of our global CPU usage through these conversions. Replacing Python is also, of course, a big win for developer experience, because now you get syntax highlighting, IDE support, linters, auto formatters, not to mention type checking. So our goal here is to completely eliminate Python from our primary code base, and we expect to reach that goal within the next few months. We've only just started converting pure Python modules to static Python, initially targeting very hot modules. We've done only around 5 modules so far, and we're already around 1% global CPU in from those conversions. So for us, these are really good numbers. They might look small, but a 1.7% global CPU in production is like a notable highlight for an entire half. And with only 5 modules converted so far and a lot of improvements still to be made to static Python, there's lots of headroom here. I should definitely set some clear expectations. Static Python is super immature, very much under construction. Most of the time when we convert a module, it reveals bugs and missing features. So definitely not a streamlined experience yet. And the compiler itself needs lots of performance work too. But nonetheless, as a sort of proof of concept of what is possible for type Python, we find these results kind of exciting. So with that caveat in mind, if you do want to play around with this yourself, it's part of our CPython fork that we've made public, which includes everything that I've discussed here. So it includes static Python, the bytecode quickening, the JIT, all of that, and you can try it out yourself. I've also listed here a few of the papers I mentioned earlier that were influential in the design of static Python. So if you want further reading, you can look those up. And that's it for me.
We only have like 3 minutes, but we could do a couple questions and then move to a breakout room.
Sorry, I talked too long.
No, that was very interesting. I see a hand. Oh, whoa.
Sure, Yella.
Yeah, so I was curious for your runtime cast, how do you handle things like list ints? Does it enforce at runtime that every member of the list is actually an int?
So I have a slide on this, which I could show. I had to cut it out for time reasons. So the approach that we use for generic types is similar to what we use for classes, which is that we want to provide, so far we've only done it for a dictionary, but we have a checked dictionary, which enforces types on set item. And then that's safe to pass through non-static code, and we know it will always have the right types, so we can trust them. And then within static Python code, when you do a set item on a checked dictionary, it bypasses the check, so it's same performance as a regular dictionary. And so we intend to provide a similar checked list. And if in a hypothetical future where Python just worked this way, those could just be the default behavior.
I see Yuka's hand.
Yes, go ahead.
That was super interesting. It actually seems pretty similar to what we do with MyPyC, which we used to compile MyPy, except for that we compile the C extension modules and it's an ahead of time compiler. So yeah. Always like the implementation technique is quite different, but like the way you do like the static versus dynamic thing seems pretty.
It's very similar, and MyPyC was definitely an inspiration. The main reason we took this approach is I think at the time we started this, my understanding or my memory is that MyPyC required like whole program compilation, which didn't work for our incremental adoption needs. It looks like now that's not true. Like MyPyC can do individual modules as part of a larger program. And the other reason is just for our dev infra team, the whole like building Python is a big pain operationally. And so eliminating a build step and just having it be part of the natural Python bytecode compilation was another motivation. But it is definitely very similar.
Yeah, that makes sense. Do you have like a completely separate type checker implementation in Cinder compared to Pyre? Is there any kind of sharing?
We do. So static Python because the needs are different in terms of what types can be trusted and all of that. Like we do have a separate type analysis, type binding, everything, which is currently very immature and limited compared to all the mature type checkers here.
Cool. Okay, I'm going to jump in here and let Rebecca set up her next talk. Do you guys want to use a breakout room? Carl, up to you if you want to jump into.
Sure, I'll go into breakout room A for anyone who wants to talk more about this.
Cool. I think there was one question from Daniel in the chat as well, if you want to address in the breakout room, but yeah. Cool, thank you.
All right, can anyone,
Yeah, but I think we are seeing the presenter screen.
Yeah.
Oh yeah, that's better.
Yeah, this is good. Okay, everyone can hear me, right?
Yeah, looks good.
Okay.
Can hear you and see you.
Cool. Okay, I want to talk about some work we did for Pyre a year ago, namely how to type check incrementally. Before we start, a bit about myself. My name is Jia. My background is static program analysis and program verification. I've been working on Pyre for about 2 years now, and if you ask me why you should choose Pyre over the many other alternative type checkers, what makes Pyre stands out in the competition, my answer to you would be really simple. It's really fast. If you go to our website, you'll find out that we're not super subtle about this point at all. Note that we are fast not just for the sake of being fast. We have a more legitimate motivation. Similar to the situation described in Rebecca's talk, the scale of type checking that we need to deal with every day at Facebook is also pretty demanding. One of our primary customers is Instagram. The Instagram server code base contains multiple millions of lines of code. And on average, Pyre is invoked on this code base tens of thousands of times per day looking for type errors. Given that Pyre is invoked so frequently, if we're not so fast, we are going to waste a huge amount of Instagram developers' precious time. Of course, we don't want that. In the past, a huge amount of engineering effort has been spent on optimizing the time it takes to do a full end-to-end check with Pyre. But even with all those optimizations, a full check of the entire Instagram server code base still takes around 5 minutes. Given the scale, this is actually not a bad number by itself, but our users like to have something more responsive than this. Many of them have Pyre connected to their IDE, for example, where type checking needs to happen live on edits. It would be a really sad experience if our user types something in the IDE and have to wait for 5 minutes before it can get any diagnostic. And this is why in practice, we rarely do full checks on Instagram. Instead, we rely on what we call incremental check, and here is how it works. The developer check out the Instagram code base, get a Pyre run on it as before. Now, after this run is finished, however, instead of throwing away all the information accumulated from this run, we persist and cache those states somewhere in memory. This, of course, still takes around 5 minutes. Now, after the developer makes some changes and want to run Pyre again, we can simply grab the cache state from memory and skip rechecking everything that has not changed by the developer. In a million-line code base, what the developer did change is typically very small compared to what the developer did not change. And that is why the second pass can be made significantly faster than the initial run. So here you go. Now you know how Pyre works from a high-level point of view. 2 observations here. One, we could persist the state of the type checker after a full check, so subsequent checks can avoid starting from scratch. And if we do this, the time complexity of an incremental check will become proportional to the number of lines the developer touches, not the number of lines of the code base. And that is how to make our customer happy, no matter how much code they have in their repository. So I hope at this point you get a sense of what I mean when I say incremental check. For the rest of this talk, I'll be trying to flesh out the idea and focus on how Pyre actually implements it. Historically, we'll make 2 attempts at the implementation, and I'll cover them both here so you get a better understanding of where we come from. Old wisdom tells us that one of the hardest problems in computer science is cache invalidation, and I very much agree on this. Incremental check is all about caching states in memory and invalidating them correctly. And this problem is indeed so tricky that we failed our first attempt at tackling it. Here is what makes the problem tricky. A good implementation of an incremental check framework needs to provide 2 guarantees. The first one is the correctness guarantee. That is, if we start a full check, cache the state, update the code base, and do an incremental check, we should get exactly the same result as if we have just run a full check on the updated code base.
In other words, incremental check should be strictly a performance optimization and should have zero user visible impact to the type checking result. Second is the efficiency guarantee. That is, my incremental check should recompute as less as possible. That's basically how it can get fast. Notice that in some sense, correctness and efficiency are in conflict with each other. The more you recheck, the more confident you can be that your type checking results are always correct and always up to date. But at the same time, the more you recheck, the slower the type checker is going to get. We, however, want to budge on neither of these guarantees. For us, incremental check has to be always correct and usually fast. So how do we jump out of this correctness efficiency trade-off and get the better of both worlds is not as straightforward as it first appears to be. Here is the solution we started in the beginning. This is how our cache is going to look like. No fancy design. A type checker just reads file from the file system and compute type errors for each file. So our cache is going to be a table like this where keys are file path and values are corresponding type errors. Now, when the user changes some file on the file system, say a.py, after which it invokes Pyre, we can just go ahead and retype check the updated a.py. Let's say that in the updated file, all type errors are fixed. We then go ahead and look up the cache entry for a.py, fill in the new values for it, and call it for the day. This is simple, this is straightforward, and this also turns out to be incorrect. Rebecca mentioned this in her talk as well. Just updating the cache entry for a.py alone is insufficient here because type errors in other source file may depend on the content of the file that we're currently editing. For example, say this is how a.py looks like, and this is how b.py looks like. In a.py, we have a function called foo, which gets invoked within b.py. Now let's say that the user edits a.py, fixes the type error, and changes the name of the function foo. Although this name change does not affect the type error of a.py itself, it does have downstream impacts on the type error of b.py, since after the modification, Pyre now needs to emit an error in b.py saying that a.foo is no longer a function. So the point here is that cache line invalidation is not an isolated process. There are additional dependencies among these cache lines. One does not simply recheck a.py just because the user only changes a.py. We need to take into account those additional files that depends on a.py and recheck those as well. Note that it is possible for changes to be cascading. For example, if a.py export function foo, b.py import and re-export the same name, and c.py imports the name from b.py, then whenever the original definition in A is removed, an error must be reported on both B and C, although C does not directly import anything from A. So to make sure that the incremental check can provide correctness guarantee, we've got to track all those dependencies by computing this kind of dependency graph where nodes represent source files, and if there's an edge from A to B, then the type errors in B may depend on the content of A. I won't go into detail about how this graph can be constructed here. Just going to say that at file level, the easiest way of doing this is to inspect import statement in each file. Once this graph is constructed, then on each incremental update, we want to recheck not just the file that are changed by the user, but also all files that are part of this transitive closure of the dependency graph. The reason why we need a transitive closure, not the direct successors, is precisely because, as I mentioned before, changes can be cascading. So this is our initial solution. It seems reasonable, it seems correct, and also avoids rechecking from scratch in many cases. So we get some sort of efficiency here. So why is the problem? Why did we abandon it? It turns out that the level of efficiency we gain from this kind of solution is far from our expectation if you try to run it on a real-world code basis. Here's the core issue. Dependency graph for large code bases will typically look like this. They're huge, and they are highly interconnected. It is fine if you're working on one of those leaf modules where no one else imports, but as soon as someone starts to reuse your module, code will just manage to import each other in all kinds of creative ways, especially for type checking, where people tend to import even more names than runtime with the if type checking trick. And this is pretty much inevitable once you get a large team hacking on the same code base. It is estimated that in some of our customers' code base, more than 60% of the nodes in the dependency graph falls in the same strongly connected component. Rechecking 60% of the file on each update is definitely not going to make incremental check time goes from minutes to seconds. So we need a faster way of doing this. To summarize the lesson we've learned so far, dependency needs to be taken into account when implementing an incremental check algorithm. Otherwise, we won't get any correctness guarantee. On the other hand, tracking dependencies at file or module level is not practical because they're too coarse-grained. In a large and complicated code base, it is fair to say that at module level, everything depends on everything else. We've got to track dependencies at a finer granularity in order to have a chance to be efficient. Let's talk about how we can fix this. How do we refine the granularity of those dependencies? Here is an illustration. This time, instead of treating the type checker as one giant black box that reads from file and emit type errors for the entire file, we break the computation down into multiple phases. And instead of having one cache table that maps from file path to type errors directly, each phase now maintains its own cache table. For example, we may have a parser phase that maintains a table from file path to the abstract syntax tree of each file. We can also have another phase that inspects abstract syntax trees and collect the annotation for each function. If you saw Carl's talk earlier, static Python is doing this as well. They call it declaration visit, but the idea should be the same. And finally, we have this actual type checking phase where we examine the body of each function and compute type errors accordingly. The point of breaking down the type checker into phases like this is to localize recomputation. Previously, computation for the same file are all bundled in this one big package. When something changes about a file, we have to go through the entire package all over again. With multiple phases, we introduce a chance to redo work in one phase while keeping everything intact in other phases. The point of breaking down the big cache table into multiple ones like this is to localize cache invalidation. Previously, if a file changes, all cache info about that file has to be invalidated. But with the granularity of cache entry shrinking down to individual functions, we get the benefit of partial invalidation. That is, if just one function in your module depends on upstream change, we just need to recompute the value for that one cache line instead of invalidating all cache lines for the entire module. Fine-grained computation and fine-grained cache line slice our original task from different axes. They are both helpful in reducing the workload during incremental check. Dependencies now work differently under this framework. Previously, dependencies are from file to file, but here dependencies are from one cache line in the earlier phase to another cache line in the later phase. For example, collecting the annotation of a.foo depends on a.py being parsed first. So we have dependency edge from the entry a.py in the parser table to the a.foo in the annotation collector table. And same goes for these other items. Similarly, we need to do annotation collection first before we can kick off type checking for function bodies, because we need to figure out the type of the callee before we can type check the body of a caller. For example, let's say in this particular program, b.bar calls a.foo. Then there needs to be an edge from the annotation of a.foo to the type checking of b.bar's body. And same goes for these other items as well. Now let's say that we changed a.py. What's going to happen next? Well, not too differently from what would happen previously. We need to compute a transitive closure on the dependency graph, except this time, the dependency graph operates on a finer granularity. Note that if we were still on a module level coarse-grained dependency tracking, then editing a.py will cost us to recheck the entire project, because if you look at the example carefully, some functions in B invoke some functions in A, and some function in C invoke some function in B. So all modules ended up in the same transitive closure. With function level dependency tracking, this is no longer the case. All cache lines that we circled out here stay the same. We don't need to invalidate them anymore because they are no longer part of the transitive closure. The win may look small on this tiny example, but imagine if you were in a large project where the majority of the functions gets untouched by any small change, the scale would much more likely to look like this. Recomputed cache line is just a thin slice, while untouched cache lines are the norm. The wins can be big here. So to recap, our revised algorithm is almost the same as the initial algorithm. We still build the dependency graph. We still compute the transitive closure. The only difference here is that the dependency graph is now not module level. But here, I was glossing over an important question. How the heck are we going to build this function level dependency graph? Going back to the already example, where do all these dependency edges come from? In the case of module level dependency, we could draw these edges by inspecting import statement, but between functions, there are no explicit import statements for us to look at. To make matter worse, both the correctness and the efficiency of the entire algorithm critically depends on how we draw these edges. If dependency graph is too sparse, that is, if we're missing edges that should have been there, we won't be invalidating enough cache lines, and the algorithm will give us stale and incorrect result when updating these functions. Conversely, if the dependency graph is too dense, that is, we're including edges that should not have been there, we will be invalidating more than we need to, and incremental check will be slowed down by this computation that could have been avoided. So how do we build the dependency graph so that it's neither too sparse to undermine correctness, nor too dense to undermine efficiency? It turns out this is surprisingly easy to do as long as we do it at the right time. The intuition is that we should forget about building these dependency graph as a separate step in our analysis and instead build them while type checking is in progress. Once again, let's look at an example to see what I mean. Suppose this is the content of a.py and this is the content of b.py. We're currently type checking the body of b.bar. While type checking is in progress, the type checker needs to look at this return statement and ask the annotation collector, what is the type annotation for function a.foo? It has to ask this question because without information, the type checker won't know if there is a return type mismatch. Let's say that the annotation collector offers the get API for this kind of query. The observation here is that whenever the type checker invokes this get API, it is the perfect time. We should go ahead and record the dependency edge immediately. To ensure at the implementation level, this very dependency between b.bar and a.foo gets recorded, a simple API level trick can be played here. Let's change the API of the annotation collector a little bit, such that the get method, which have access to the cache table it owns, forces the caller to specify the dependent. In other words, if you want to know what is the annotation I collected for this given function, you have to tell me which function you are currently checking. This way, the get API here gets the knowledge of both the source and the target for this particular dependency edge, and we can programmatically make sure that it records the dependency edge before returning any lookup result. Zooming out to the big picture, the previous slide showed you how we can program Pyre in such a way that this dependency edge always gets recorded when we're type checking b.bar. Other dependency edges between the annotation collector and the type checker can be added in similar ways when we were type checking other functions. As long as data access to this annotation table is gated with the modified get APIs, we're golden. The exact same mechanism also applied to any dependencies between the parser and the annotation collector. If dependencies are dynamically constructed this way, we can be sure that any edge that actually exists will be recorded due to the API enforcement, and we can also be sure that any edge that does not exist will not be recorded, since we'll just never query for the information in the first place. So now we know where the dependency graph come from, and that should be the final piece we need to complete the entire puzzle. Now, before I conclude this section, a few more words about implementation. Up to this point, everything I described about the internal Pyre are highly simplified to help communicating the high-level idea across. But the real Pyre implementation is far more involved, since it has to deal with far more complexities. For example, in our simple model, I only mentioned 3 phases, but the real Pyre is 3 times larger than that. This is because the real Python language is not just about modules and functions. We need to understand type aliases, class hierarchies, global attributes, decorators, descriptors, and many, many more stuff. Also, there is massive amount of parallelism behind each phase. Populating individual entries in each cache table can be very efficiently parallelized, and we also have fancy concurrency-aware data structure to support all these parallel operations. And finally, representation of dependency edge are highly optimized as well. A dependency edge only takes around 8 bytes in memory, and with that, our dependency tracking system managed to get a very small memory footprint overall. The bottom line here, there's non-trivial amount of engineering work spent on this system, since we're very serious about making Pyre fast. So in the end, how well did we do after pouring so many engineering hours into the revised solution? Remember, I said before that an end-to-end full Pyre check takes around 5 minutes to run on Instagram on average. With incremental check, the average number is down to 3.9 seconds. In other words, incremental check yields more than 100 times performance improvement. And 90% of the time, no more than 170 function is going to be rechecked every time a Pyre incremental run is invoked. In addition, since we switched to function level dependency tracking, we have not heard from our user complaining about Pyre incremental check being inconsistent with full check for quite a while. In contrast, incremental inconsistency was one of the most frequent issues our customer ran into back in the day when we were still on module level dependencies. So correctness was now sacrificed for the performance thanks to the API enforcement trick I mentioned earlier. And of course, no system is without limitation, and Pyre is not an exception. Phase type checking and fine-grained dependencies are nice, but this design does impose some hidden restrictions on what we can do and what we cannot. If you pay close attention, you'll notice that our fine-grained dependency algorithm tried very, very hard to avoid forming cycles on the dependency graph. Phases must be carried out linearly, and dependency edge can only go from earlier phase to later phase, so cycle is never possible. This is actually an intentional design point. Having dependency cycles will get us into this funky situation where getting the type error of this function indirectly depends on getting the type error of this function itself. What should we do in such cases? Should we recheck the function? Should we not? How many times should we recheck the function? Do we compute a fixed point of some sort? How can we even guarantee that a fourth fixed point even exists? These are hard questions that we would really like to dodge, hence the no cycle constraint. Such a constraint in turn limits the flexibility of the system. Certain tasks that requires interface fixed point computation like global type inference is just not possible to do with our framework. And certain other tasks that requires intraphase fixed point computation like type resolution and decorator resolution are possible, but cannot be done very efficiently. That being said, these limitations have not become that big of an issue for us so far, so we're happy with what we have today. Takeaway of this talk, the key to make a type checker fast is to do things incrementally. The key to do things incrementally is fine-grained dependency tracking. And to implement fine-grained dependency tracking, our approach is to organize the type checker into multiple phases and use multiple cache tables. Extra credit goes to Mark. We worked together on this project, and we also want to thank the hack team at Facebook since we reuse a lot of their code. That's all I have today. Happy to take questions and comments. Also interested in how this problem is tackled in other type checkers. Thank you.
Jukka.
Thanks for the interesting talk. So I can talk about how we do this in MyPy. So MyPy also tracks like fine-grained dependencies using the daemon mode. But we have a separate pass which calculates the dependencies. So that's a bit error prone. So that's actually a clever trick that you explained. I wonder whether we could have used it. So we really had some issues with like missing dependencies. So we so what we did is we kept run all the increments over like a period of time, looking at all the commits, and we checked whether like the file level incremental mode and the fine-grained incremental mode would generate the same results, and that's how we kind of found out about some deviations. And I guess one more thing that has been successful for us is we use remote cache downloading, so an incremental loading of like cache snapshots for the full builds. And so when a user does a cold run, they download the most recent cache, or or maybe apply like incremental diff from a previously downloaded cache, and then we run an like fine-grained incremental check on top of the cache. The cache is generally a bit stale, so because it takes a while to build it, so it might be like say 20 minutes stale. So then we apply like 20 minutes of changes incrementally, and that way, like generally we can do like the cold run in about like 1 to 2 minutes over several million lines of Python. But this assumes assuming you can download it fast enough. So it might be a bottleneck if people are working from home.
Yes, I think we do a couple of points here. First, yes, I think the point that if you have a robust enough incremental check, you can use that plus some checkpointing to speed up cold start. We do that in Pyre as well. I think what we're doing here is quite similar. And yes, we also do this testing where we collect a bunch of commits and do this scan through the commits and check whether there's mismatch between incremental result and full check result. I think when we're trying to implement this system, we're doing the same thing here. So it's glad to know that great minds think alike.
Very cool.
I think there's a couple questions in the chat actually. Is it easy for you? Yeah. About dependency cycles and then type annotation. Yeah.
Yes, it is possible to short circuit graph traversal if type annotation doesn't change. This is one of the optimizations we do. If this thing doesn't change, don't compute any downstream transitive closure for it. There's no point in doing that. We also have this another optimization where we populate things lazily, but if anyone is interested, I can explain this offline. But yeah, those optimizations are really important. I think the short circuiting will get us like around 50% performance improvement. That was really huge there. What do we do if there are dependency cycles? We forbid cycles. Cycles is, like I mentioned before, cycle is, we don't know how to handle it, so we just forbid that in our system. It would be interesting to see how the system would look like if we allow that, but at the moment, it's just too complicated. So the question is, do we emit a diagnostic if we detect a cycle? Well, the thing we do here is that by construction, cycle is not possible. Like if you look at how our API works, like all phases are like laid out linearly, right? But there is no way you can like create a dependency edge from an earlier phase to from a later phase to an earlier phase. Like at the API level, this is just impossible.
Okay, great. I think we're at time. Thanks for the talk. And if, I guess, again, it's a break. So depending on whether people want to hop into a discussion room and ask more questions, that's an option, or you could do this like when we get back. But yeah, we'll start the next talk again promptly at 10 past. And I do remember seeing in chat there is some interest in a breakout room specifically to chat about, I think, like type annotations for new Python users or like syntax readability. We could either do that now, like during the break, or if people have time after, there is like a nice platform I have that we can move to that allows like simultaneous group discussions. So that's also an option, just a heads up. But yeah, breakout rooms available. Otherwise, see you guys at 11:10.
For those who are interested, I propose we move to discussion room D for the discussion about type annotations and beginners, just to keep the space here quiet.
Sounds good.
Oh, now I have the problem of like figuring out how to join a breakout room. What is the magic incantation?
So if you hover, so first there's a big button at the bottom that shows all of them. And then if you hover the number of people, it turns into a join button. I don't know why Zoom did that, but does that work for you?
Oh, yes. Well, so thanks.
So Shannon, did we want to talk about the social hour at the end?
Oh, yes. Oh gosh, I maybe click join. Okay, I'm not moving. Yeah, I'll maybe mention it right when everyone gets back.
Okay.
Cool. Good.
So my name is Jukka. I'm going to talk about scaling Typeshed to 1,000 packages. So the talk portion is not going to be that long, so there should be plenty of time for discussion. So hopefully, so think about questions and objections and everything else while I'm presenting. In a perfect world, we'd all want to be able to catch 100% of all possible type errors statically, but clearly that's not always possible. And sometimes they're like pretty far from that ideal. First of all, like the type system can represent everything you can do in a dynamically typed language. So clearly we can always like improve the type system, but there is going to be some gaps. And even with a really fancy type system, Python is a dynamic language. So there's some dynamic language features, such like modifying things at runtime, also some library features, and some libraries have things that are kind of really hard to model using static type checking. So we have to resort to any types and other things from time to time. But finally, every non-trivial Python program probably depends on some third-party libraries, almost always, and at least a standard library. And for those, we generally need stubs because most libraries don't have annotations. And those, if you don't have good types for the libraries, then obviously type checking is going to be seriously compromised if you heavily rely on some libraries. This is going to be my focus of today's talk. Like, how could we improve the stubs for libraries? So I did a quick analysis of the top 1,000 most downloaded PyPI projects that you're going to pip install. And I looked for whether they ship with types. So they can like type checker should be able to like just use like ship like either stubs or inline annotations, or whether these have stubs in Typeshed. And about 100 of those had the py.typed file, which means that the library, or the module declares themselves as being TypeShed compatible. 68 had stubs in Typeshed. But over 80% of these didn't seem to have types. Some of them probably had some, somewhere in a separate repo might have some types, but probably not most of these. So the vast majority of code is kind of missing types, at least for libraries. So, and if you look at Typeshed, obviously, there's only 85 third-party projects included. So clearly, it was kind of there's no hope from the beginning. So I wonder if we could do something about this. And this is actually something I talked, it was like 2 years ago, Typing Summit. So, and things kind of still are looking kind of pretty bad from my point of view. So I've been thinking about would it be possible to get 1,000 packages or projects in Typeshed? So what could we do to make that possible? Now here's some ideas I came up with. First is we shouldn't start with perfection. So let's accept the fact that initially we'll have some pretty janky stubs. I'll call them baseline stubs. So these stubs with minimal or no type annotations at all, just like skeletons where you can kind of add things. But if you can make it easy to do these, maybe it's a good starting point. Additionally, it should be easy to contribute improvements to stubs, because I think the crowdsourcing is the only feasible way, unless somebody comes up with an army of contractors who can fill in these types, because there's a lot of surface area. Third, it needs to be easy to start using the latest contributed stubs. So if people are using MyPy and MyPy has a release in 2 months, they don't want to wait 2 months for their contribution to be available for them. So that's too slow. And also, if you want to increase the activity on stubs, we need more Typeshed contributors. We can't expect the current set of contributors will just kind of 10x the volume of contributions. So definitely that's something we should be able to solve if you want to fix this problem. And finally, now we talk about these baseline stubs with no type annotations. Maybe you can auto-generate them. So maybe you're going to bootstrap the whole thing mostly automatically. So this is kind of the gist of this talk. So I think all of these kind of seems like should be possible, at least worth a try. And actually, making it easy to use latest contributors, that's already kind of possible, because a few months ago, we changed the structure of Typeshed. And at the same time, we started uploading stub packages to PyPI for all third-party packages in Typeshed. So basically, the moment you land a pull request, you'll get a new package that you can install and start using. So this is what I've been calling modular Typeshed. So if you create a new third-party stub package, Typeshed, or create an update, it gets automatically uploaded to PyPI. So there's no dependency on type checker release cycles, and type checkers don't need to ship with everything, which means that if there's some bad stubs or some bad changes to stubs, then they won't users don't have to deal with those, or we don't need to do point releases for bad stubs. So I think that's kind of a key change that kind of enables the other changes I'm kind of hoping that might happen. Okay, I mentioned baseline stubs. So these would be automatically generated, because realistically, we can't expect people to manually start writing stubs for non-trivial libraries. It's just too much work and it's too error prone. Luckily, we have a tool StubGen, which MyPy ships with, which does a pretty good job of generating exactly kind of these baseline stubs. And so these don't have any type annotation. So this is kind of roughly how they look like. So you have just anything is type any or missing an annotation, but you get attributes, classes, and functions. So this is kind of still a starting point. Okay, so now I'm going to be thinking about, hey, if it's any type, is it actually any value to having these stubs? Because I guess we can't use them for type checking, right? Actually, this is enough to do some basic type checking. It is actually quite a lot even. So for example, you can catch typos. If you import something, you can check that it exists, it's correctly spelled. If you call a function, you can check that the name is correct. You can check whether some C is a class that can it be used as a type annotation, because using a function as type annotation is kind of silly. And you can check the base classes of classes. You can like follow like MROs. You can see which methods and attributes are defined and stuff like that. So there's quite a lot already. And you can, when you call a function, you can check like whether keyword arguments are compatible, whether there's the right number of arguments and stuff like that. And maybe even more importantly, once we have the baseline stubs, and the barrier to improving those stubs, like contributing like further pull requests, which like say add a type for a function, or like a return type or argument type something, those are pretty easy to do, because you just like find somewhere where there's any missing type, and then you just add some type, and that's it. Whereas coming up with the initial set of stubs, that's kind of scary, because it could be like hundreds or thousands of lines of code. So even if you auto-gen it, you might not trust it if you're just starting with. So this, I think it makes it much easier for non-experts to start contributing by providing the baseline stubs there as like the basis, or well, baseline. Okay, so let's see. If you assume that these baseline stubs would be helpful as such, and would also kind of get more people to contribute improvements to stubs. So I think it would be used to have a really easy way to generate these. So I've been thinking, and I think it should be possible to have write a tool. I'm actually thinking of like contributing one myself, that could, like, given a name of a PyPI project, it could generate a pull request that adds baseline stubs for that project against Typeshed. So it would run stubgen to generate stubs. First, we actually need to install the package or distribution, and then we run stub test, which is another tool, handy tool, which kind of validate that stubs kind of match what is available at runtime. So you might be able to leverage that, and then we can use Black to auto format the stubs to look nice, and then finally we can create a pull request, or at least create a branch with the changes. So that all seems kind of doable. There's like some edge cases and stuff, like what if something goes wrong and stuff. So it needs to be user friendly. So it's kind of not entirely trivial, but it doesn't seem that hard. And once we have this tool, maybe we could just run it against like 1,000 packages, and just, you know, commit all those, everything that kind of looks reasonable, it doesn't fail along the way. Maybe we can just add these to Typeshed as the, you know, the baseline for these projects. Well, it's not quite that easy. So obviously, if there's like, say, pandas, it's like a huge API, and it probably, you probably want to do some due diligence. It's already very popular. So, but at least for the many third-party projects are pretty small. They have maybe just a couple of modules, maybe a few dozen functions. It seems like, yeah, we should be able to deal with those. And maybe some of the larger ones need some due diligence, and we need to filter out whether we don't include a ton of internal stuff in the stubs that aren't actually part of the public API. So that's kind of the what I think that might be feasible. Obviously, I can see there's might be some problems with this, and here's some like I'd like to discuss these because we should still have, yes, we still have quite a lot of time. And here are some things that might kind of be problems or some of the open issues. So first is like, how do we determine which are the top 1,000 or whatever number we choose packages? Download sets might not reflect reality of like popularity, because there might things like CI systems which might kind of bias those results. I think dependencies of packages also included as downloads, but if it's a dependence, you probably don't care about it as much. If you have dependency for a hugely popular package, then you might kind of go pretty up, as far as I understand. And then maybe the auto-generated stubs, are they high enough quality that we can just blanket like commit them without too much review, or should we still be a bit more careful and actually try to get like a small number of high quality packages instead of like large number of unknown quality packages? Or maybe move gradually, as I first started with like a 50 and then see whether things work out and whether people complain and find them useful, and then gradually increase like a 200 and so on. Yeah, unclear. And then maybe instead of having like any types, could we actually implement some type inference or use some existing tool that can do type inference for us, assuming it's reliable enough so that we can have like return types and stuff in there instead of just any's. And again, like once we have these stubs, they are, as I mentioned, I argue that they are still useful even if they don't have many types, but it would be even better if we could actually find people that would contribute and start improving those, provide pull requests that add to the types, at least for the most important APIs, because many libraries only have like a handful of APIs that are mostly used. So just a small number of function annotations might go a long way to making like stubs more useful. And then there's a question, if you are very successful, we have 10x more stubs in Typeshed, we might have like 10x more pull requests, and then we might have enough bandwidth to review all of those stubs. Okay, this might be a problem. On the other, I think that's like a good problem to have. So it's better to have that problem than not having enough stubs. So I think it's still kind of an improvement of this current status. Okay, so please, that's all I had. So that's my kind of idea of how we might be able to get to 1,000 packages or any number of packages on Typeshed.
All right, looks like there's some hands. That's Ethan.
Yeah, thank you, Jukka. I definitely think this is a very, very important topic to discuss. I think one aspect of this that I think will be very important going forward is, regardless of what method we decide on, whether to centralize in Typeshed or to kind of push package maintainers to have their own types, which I am less sure of as a possibility. Regardless, I think it's also very important to think about. I think a lot of the popular packages have very dynamic behavior and probably will need plugins for most type checkers. And so I think we also should, an important part if we want to have types for the most popular packages is to maybe talk about what a shared plugin ecosystem might look like. Anyway.
Yeah, that's a good point. I guess about plugins, one option would be to provide a way of giving dependencies to stub packages for all the available plugins, and make sure that even the baseline stubs are usable without plugins. So the plugins will just kind of improve the quality of types, but it should still be feasible to use without them. Otherwise, I don't think we can include those stubs in Typeshed.
Eric?
Yeah, I mentioned this in the chat, but I wanted to make sure that we had a discussion on this. The question I asked in the chat is whether the real long-term goal is to get lots of stubs in Typeshed, or whether it's really to get py.typed packages. I've always thought of Typeshed as kind of a bootstrap, kind of like definitely typed was in the TypeScript world. And that serves a really important purpose. But I'd personally rather see us really push for getting package authors to own type information, whether it's package stubs or whether it's inline types. There are lots of benefits to that. It scales much better. So I just wanted to see if others agreed with that long-term vision.
I agree with that. This is because looking at the current data, Python-typed isn't that popular yet. So I think this is a way of bootstrapping the stub ecosystem. So giving kind of like getting some basic level of functionality in, and then hopefully this will attract more contributions. And then if there are stubs that are high quality, maybe projects will be happy to kind of upstream them. But things like it's not scalable to start talking to like hundreds or thousands of owners about, hey, would you please add types to your project? So I think this is much more efficient use of time right now. And then afterwards we can try to work with long play could be, and definitely I think should be that most important libraries will ship with types, but it's unclear how feasible that is to me.
Sebastian?
Yeah, I mentioned that in the chat as well. My personal long-term vision is also to see Typeshed more as a bootstrap thing, and to get type stubs into libraries and maintain them with the libraries. But another thing I mentioned is the idea of the types code, which I would plug here now and maybe work on it to have a place where people who are not experienced in types, and because types are very complex for some libraries, can get help with their libraries so that we can get high quality stuff into those libraries and don't have to rely on Typeshed and as Typeshed maintainers to review those in Typeshed. Because I think at the moment, because we are quite experienced in Typeshed with reviewing stubs, that the stubs we get in Typeshed are probably fairly high quality, as opposed to people who are not experienced with stubs putting them in their own libraries necessarily. And so we have a place where we can help those people who want to put stuff into their own libraries and are struggling with it. And yeah, I just want to ask whether that's a good idea, and well, yeah.
Yeah, I think that's a good point. So I think I've heard somebody did the study of type annotations in like open source code, and apparently a lot of it doesn't type check or something. Maybe somebody can remember more about it. I think there's some study or blog post or something about this. So it's possible that a lot of types are not actually validated. People might not know how to do it properly. They just like use like intuition to annotate their code, which might not be very useful for type checking purposes. It might be good for documentation, but that's kind of not good enough for us.
Guido? Oh, you're muted, I think.
I'm so clumsy. I wanted to bring up the issue of type checker extensions, or what to do about things that can't be typed with the current type system. And I know Eric has some thoughts about it. I think that there are also some good sort of proposed extensions to the type system in the 2 talks that are still coming. But that seems an important part of the puzzle.
Yeah, so if you could, yeah, this is something. So MyPy has a plugin system. It's pretty ad hoc. It's basically you can hook into the internal APIs of MyPy, and you kind of change the invert types and stuff like that. It's reasonably effective. There are a bunch of MyPy plugins available for different use cases, and I know that some projects have like their custom plugins that they use internally. But yeah, it's definitely not kind of like a very sustainable thing. It doesn't kind of, even though it might work reasonably well for MyPy, but then the problem is if you're using like an IDE which doesn't support these plugins, then the IDE kind of the autocomplete and everything doesn't kind of match together with MyPy. And also like we're kind of stuck with all the kind of, you must treat like most of our internal APIs as kind of public APIs, because who knows what the plugins might use. So definitely come out. I wonder, yeah, maybe we can come up with some way of writing plugins which have like a very specific kind of input and output that would be able to support by multiple like tools. Anyway, that's worth investigating. It might be tricky though. Are there like more discussion in chat? So let's see.
I'm curious to bring up something that I think Stephen mentioned in chat, which was, I guess in addition to or in the same spirit as a type school, is there any interest in some kind of common or open source documentation for the type system? So I think right now type checkers do their own thing. I know, like, how do we manage things across type checkers, both with regards to like extensions or plugins, or all these other things have been like on people's mind as well. But I was thinking maybe one place to start that would also help with people who want to onboard their project and don't really know where to start is like some kind of common type system documentation with like examples and yeah, just like a better source of truth. Curious if people have thoughts about working on that, or trying to get something together from existing documentation that is type checker specific.
Yeah, we discussed this a bit recently in the context of the fact that PEP 484 is still technically provisional. I suggested that we should write some general documentation for the type system to replace the things that are currently scattered in various PEPs. I'm interested in working on that, but I'm not sure I'll get around to it very soon.
Would it be, I guess, how would it be distributed? Would it be part of the Python documentation, or would it be like a separate thing that could be?
I guess making it part of the Python documentation makes sense to me, but perhaps we can first start it in like the typing repo and then put it in a separate read to docs website or something.
Yeah, I've also dropped in the chat a link to the new docs community repo in Python. And so that could be a place that, if you want to put ideas, even in the short term, we might be able to come up with some guidance for and messaging.
Well, we have about a minute left.
Okay, in chat is, yeah, Eric mentioned that. Okay, Eric.
I was going to mention one topic that's somewhat related to Typeshed, but more applicable to the PyType inline types is the notion of type completeness. So once somebody marks a package as py.typed, we're kind of at the mercy, given the way that py.types override other stub files. And so if it's very low quality, it really hurts the experience. So in Pyre recently, well, about 6 months ago, I added a mode where you could run Pyre over a py.type package, and it produces what I call a type completeness score. And it calculates that just by finding all of the public symbols, all the classes, methods, type aliases, etc., in a py.type package, and specifies how many are completely typed. So, if it's missing an annotation, obviously that wouldn't be in that bucket. And the percentages vary immensely across py.type packages. I'm seeing everything from 100% down to about 5%. Jake mentioned in the chat that he's thinking about implementing kind of a dashboard that keeps this up to date, which I think would be a good visibility, good incentive, where we can incentivize package authors to really continue to improve their type quality. The good news is I have seen those percentages continually go up over the past 6 months. I run it manually periodically on the top 20 or so packages, and I'm seeing continual improvements. So that's a good sign.
All right, cool. Let's switch to the next talk. And if you want to jump into a breakout room, Jukka, that's also an option. I think they're all free. So maybe been reminded to give people a heads up. I was going to do this during the break, but in about an hour, we have like some time to socialize. And if people want to like order food or a drink or something, like just a reminder, you could maybe do it now if you want it in time. But I think that's, yeah, that's it. Pradeep and Matthew, are you guys ready? All right.
Are you able to see the screen?
Looks good to me.
So let's get started. Today we want to talk about catching tensor shape errors using the type checker. So about us, I'm Pradeep. I work at Facebook on Pyre, which is Facebook's type checker for Python. Matthew is a research engineer at DeepMind. He works on safe reinforcement learning. So let's say you're a machine learning engineer. You want to write an image classification program that distinguishes cats and dogs. So you write an initial model and you send it to the cloud. So a few hours later, you get back your results and okay, you've successfully distinguished cats and dogs, but you aren't quite happy with its performance on, say, memes. So you use a slightly different model and then send it to the cloud again, right? Now you wait for a few hours, but this time you find out that the job actually crashed. Turns out you hadn't updated the evaluation code, and because of a simple dimension mismatch, the entire program crashed. So this seems wasteful. Like, what if we could catch such mismatches and shape errors upfront and fix all of them before going into this long iteration cycle? So in this talk, we will outline one approach that we believe can help you do exactly that. So we'll talk about tensor shape errors and why we care about catching them. We'll propose a way to catch these shape errors without running the program using what we call tensor shape types. We'll walk through a few examples of how this works in practice and point out its limitations. So by a tensor, we really just mean a multi-dimensional array containing elements of the same type. So this is a 3-dimensional tensor with shape 2 by 3 by 4. So you could create it using, say, torch.rand in PyTorch with arguments 2, 3, 4. So that would give you a tensor like this. Or you could use NumPy to do the same thing. This sort of data structure is widely used in machine learning. So in our cat and dog classification, for example, we would accept a batch of training images as a tensor. So it would be like a batch, height of the image, width of the image, color channel. So these would be the sort of information that we would have within our tensor. So just to sort of assure you, if like me, you don't know much about tensors, there's no need to worry. This talk is not about the tensor operations or the math involved. It's all about the shapes, the dimensions 2, 3, 4, things like that. Definitely no deep math. So a machine learning program performs various operations on a tensor, possibly producing a tensor with a different shape. So for example, here's the linear transformation. For our purposes, it's just a black box that takes in a tensor and transforms the last dimension. So in this case, it expects that the input will have the last dimension as 2, and it guarantees that the output will have the last dimension as 3. Now, if we create a tensor with shape 4, 2, and sort of feed it into this linear transformation, we will get back a tensor of shape 4 by 3. So the 2 at the end was replaced by a 3. So this is an example with 2 dimensions. This works for any number of dimensions. So what happens if we pass in a tensor with shape 4 by 1? We know that it expects 2 as the last dimension, so it will blow up at runtime. So this is what we refer to as a shape error. And a linear transformation is just one kind of shape transforming operation. There are any number of tensor operations, all of which have some requirement on the input shape and some guarantee about the output shape. So why do we care about such shape errors? So people have found that confusion about tensor shapes and broadcasting is one of the most common classes of programming errors when you're doing machine learning or tensor code in general. To put some numbers to it, Matthew ran an informal survey at DeepMind, and he found that half of the errors that people ran into when prototyping their work was because of tensor shape errors. And when they ran real experiments, these accounted for about 10% of the errors. But clearly, it would be worth detecting these bugs upfront. So why might shape errors occur so frequently? It's hard to reason about the shape of a tensor as it gets transformed over multiple operations. So we don't need to know the details here, just that these are 3 different operations. And when you pass a tensor through each of them, it can be hard to tell just by looking at the code what the shape of y is. Like if I pass it to linear, will it blow up at runtime? It can be hard to tell, especially as the program grows more complex. Second, it's easy to regress existing tensor code. So a lot of tensor coding happens in an explorative setting where people may not unit test each function. So even if you do test your model end-to-end initially, a later change may just break it in a subtle way. And as we saw in our example, it can take hours to even realize that there is a shape error. So this iteration time can be really long, even if you use a mini batch of input. So given these problems, we believe that catching shape errors upfront would be a significant productivity increase for machine learning programmers. So how might we catch them? Type checking is one approach. For a quick overview, let's take the simple Python function that appends hello to each element of a list. If you call it with a list of integers, it will blow up at runtime. We all are pretty familiar with this. Type checking allows you to say that I expect the list of input to be a list of strings. So you can encode the type in your program. And if you run Pyre or MyPy, you can see the error without running the program. The advantages are pretty obvious. Like we can catch regressions no matter where we make changes. So if there's a list of strings and we use it somewhere deep within our code, and somehow later we change it to a list of integers, we would catch errors no matter where they occur and whether they are in some rare branch that we haven't yet tested in our unit test, right? So if type checking is useful, why not use it for tensor code? And a lot of people have requested that. This is the most liked NumPy issue on GitHub. It's been requested for years now. So ideally, we would do something like this. Like when we had a list, the generic parameter encoded the element type. So a list of integers was typed as list of int. Now we want to encode the tensor shape within the type. So let's look at how that might be in our linear example. So we constructed a linear object with 2 and 3. So these are key shape related parameters, right? We want to store them within the type. So we might do something like linear 2, 3. And when we created an input, we created it with parameters 4 and 2. Again, these are key types. We want to store this within the generic parameters. So we would want something like tensor 4, 2. And somehow when we apply linear to this, we want to be able to infer that the output must have the tensor shape type tensor 4, 3. So if we can somehow capture the shape within the type and follow it as it's getting transformed over the program, we would be able to catch shape mismatches. Likewise, if somebody passes in something of the wrong shape, we would be able to catch it instead of blowing up at runtime. So the ideal is that we would get a type error saying you've passed in a tensor with the wrong dimensions. The first roadblock is that tensor 4, 2 is not a valid type. 4, like you can't just use raw numbers. So the solution to that is to use literal types. You can encode 4 as literal of 4. So this lets you specify the shape within the type itself. The deeper problem is that a tensor can have any number of dimensions. But when we specify a class, we have to specify exactly upfront how many parameters it has. So this would mean having a separate tensor class for every single dimensionality, right? And if you had each of these, you would have to, for example, if you want to write a linear transformation, you would have to write one for each of these classes, which is tedious and bad software engineering. So in PEP 646, we had introduced variadic tuples, which capture an idea of any number of types. Now we can write a single class tensor with which is generic over the data type, which could be float or int64, and star dimensions, which stands for any number of types. It's like the star args in a function signature, which says 0 or more types can be accepted. So how can we use that? If you want to represent a 2D image, you can just use that as tensor int 640 by 320, a 0-dimensional tensor, a 4-dimensional tensor. These work as expected. And type checking would be like, if you create a tensor of shape 640 by 300 and you try to pass it to a variable that has the shape 640 by 320, that's a type error. So that is the basic approach we'll be using. So let's look at some examples of real world code. So if you look at the linear class, this is the definition without type annotations. It accepts the in dimension and out dimension as we saw. And its dunder call method takes in the tensor and returns the transformed tensor. With shape types, first we have to store the shape within the shape related information within the generic parameters. So here, linear cares about the in dimension and the out dimension. So you store that as one of the generic parameters. Second, in your constructor, you specify which of the parameters correspond to which of the generic types. So if you pass in 2 or 3, you know that 2 will match the in dimension and 3 will match the out dimension. And this is the key part. So the dunder call method is where we specify what we expect from the input. We expect any data type, any number of leading dimensions, but the last dimension must be in dimension, which was specified in the constructor. And if you give us an input tensor like that, we guarantee that the output would be the same data type, same dimensions, followed by the output dimension. So for linear 2, 3, we can see that we're instantiating 2 and 3 as a type throughout the class. So what happens when you call it with a tensor of shape 10, 15, 20? So when we pass this into linear, we try to match each element of the given type with each element of the expected type. So first we check the data type. Float can be accepted for D type, so there's no issue there. Then we check the suffix. So 20 can be passed to something that expects 20. So again, there's no mismatch. Finally, the in-between elements are all matched against star dimensions. So overall, there is no mismatch. We can be confident that there won't be any shape error at runtime. And using the match that we got, we can instantiate the return type to get tensor float 10, 15 from the star dimensions, and 30 from the last dimension. So in a sense, we've captured the runtime shape transformation using a type transformation. So here's the key test. Can it catch a shape error? So now I'm passing it a tensor with shape 10, 15, 21. This time when we try to match each element, we find out there is a mismatch and we raise a type error. So this is how we sort of catch runtime shape errors ahead of time. Now you might be thinking about more complicated tensor operations like convolution, which we would need for a cat and dog classification. So a convolution doesn't just replace dimensions. It uses a much more complicated formula. So you don't need to understand the math I'm showing. Just know that this is what convolution uses to compute the output shape given some input shape. So it uses this arithmetic. So even experienced machine learning programmers can't compute this in their head. The good news is that with type level arithmetic, the type checker can compute this result automatically. So if you construct a convolution operator with these parameters, and you pass in a tensor of shape 2, 10, 3, and 4, then when you apply the convolution to this, the type checker infers that the shape is now 2, 20, 1, and 2. So this is basically an experimental feature called type arithmetic that lets you do addition, multiplication, division on variables. In the next session, Alfonso will go into the theory behind both type arithmetic and broadcasting. So far, we've talked about how the type checker can catch shape errors after you've written code. So how can it help you as you're writing it? So let me give you a small demo. This is a snippet from a PyTorch program. All we need to know is that it has a bunch of tensor operations and it's passing the input through them. So first we can see that it's a function that expects an input of shape, say 1, 3, 1080, and 1080. If I hover over the variable, I can see the shape type inferred at that point, which is 1, 3, 1080, 1080. After the first set of operations, we can hover over the variable to see that it's a different shape. It's 132, 1080, 1080. You can now hover over any variable within your function and see that you can see the shape of the tensor within that part of the code, and so on throughout the rest of the function. So at the end of all these operations, we see that the shape happens to be 1, 3, 1080, 1080, which matches the expected return type. So this function shape checks correctly. Now, what if I make a silly mistake and use the wrong shape somewhere in between? So I change it to Y1. As you can see, it flags the error immediately and complains that the shape doesn't match. So the error is a bit hard to parse, but essentially it's saying that the dimensions were wrong. So, and this is not just for a function that expects a concrete shape. So let's take a function that accepts arbitrary tensors. So here's a simple one that takes in a 4-dimensional tensor with any 4 dimensions, n1, n2, n3, n4. Now, the reflection pad is just a simple operation that adds to each dimension. So if I hover over X, I can see the shape n1, n2, n3, and n4. After the first operation, the shape is now n1, n2, n3 plus 4, n4 plus 4. After the second operation, again, it's a different shape, n3 plus 24, and so on. And at the end, we check that the type we got is the expected return type. So quick note, there's nothing special cased here for tensors or PyTorch. The concept of shape types applies to any structure with arbitrary dimensions, whether it's NumPy arrays or TensorFlow tensors. The same feature can be used without any change needed. So far, we focused on what shape types can do and how they can help you catch errors. Let's look at what they can't do. So I'd mentioned that the approach was to capture shapes using types and runtime shape transformations using type transformations. Sometimes operations are too dynamic, by which I mean, say the shape is not known without running the program. So for example, if you load a tensor from a file, there's no way of knowing in advance what the shape is. So in that case, you have to specify the shape yourself. Like we can't figure it out just by looking at the code. Second, if there's a operation that works with a list, say for example, if it concatenates a list of tensors to be 1, we can't help that because we don't know the length of the list. So the list data type doesn't encode its length. So in general, tuples are preferable to lists because tuples give you an exact length. Another limitation, feature we don't have right now is slicing. So we can't support cases where you can just slice parts of a tensor. That's because we would need to store like the slice information within its type. It's not yet implemented. And a sort of sequential is like commonly used model where you sort of combine a bunch of models into one. And again, this is not something we support yet. One limitation I want to point out, and which we discovered when sort of testing it out, is verbosity. So here's a sample PyTorch program. You don't need to know what it does. It's just an example. Without annotations, this is what it looks like. If we add shape types, we can see that it does grow longer. The main differences are, one, you have to specify the shape-related parameters within the generic parameters of the class. Second, you have to specify the annotation for each parameter. That's a second sort of cause of verbosity. And mainly, you have to specify what the expected input shape is and what the computed output shape is. So this can be more verbose than sort of just writing code straightforward. But note that the method body itself remained unchanged. It's mostly the function signatures that have to specify extra shape information. And sort of definitely want to set expectations that this is still experimental. We only tested it so far on smaller PyTorch programs. The more we sort of test it on real world large projects, the more the hypothesis will be validated. And we do plan to improve the quality of life when using it. So if you're excited about shape types and you want to try it in your project right now, you could use Pyre, which supports variadic tuples for shape types and type arithmetic for transformations. Pyre currently supports variadic tuples as well. And sort of to give you an overview of the road ahead, variadic tuples was submitted as a PEP 646. Type arithmetic is yet to be formalized. It's still experimental right now. To be useful, libraries would need to add shape types to their stubs. So whether it's PyTorch, NumPy, TensorFlow, we've created some examples to get things started and for our own testing. And finally, I know many of you maintain tools like MonkeyType, PyAnnotate, PyreInfer, which automatically add types to untyped code. If we can extend them to automatically infer and add shape types, then we could easily drive adoption in large machine learning code bases and improve productivity. Thank you.
Brandon?
Hi, Pradeep. Thanks for the great talk. I enjoyed hearing about these new features for shape checking. I'm just curious if you know of a way, or you think it might be useful to have like a gradually typed interface where maybe you don't, like for the cases where you said it's dynamic, you might not know it until runtime. Would you be able to provide an unknown shape there and then have a gradually typed interface? Thanks.
Right, thanks. Yeah, I cut out some stuff from the talk. In some cases, like if you have a code that loads from a file or concatenates stuff, you could teach the type checker by giving it the type that you expect it to be. So that's one way. Another is if you have, say, existing code, you can gradually sort of migrate it. It doesn't have to be all or nothing. So for example, if your code currently just uses tensors without shape types, the PEP specifies that it'll be treated like an arbitrary sized tensor. So it'll be compatible with any function that expects a precise shape type. So there won't be any error. So you can sort of start adding better shape types to parts of your code and then so keep expanding that over time. Does that answer your question?
Yeah, I think that's kind of one way to do it, where you have just the output is completely unshaped.
Mm-hmm.
Another case might be where you do some contraction over an unshaped dimension, and then that might disappear later in the computation. So you could restore a shaped output type. But that's an interesting direction you're taking it. Yeah.
Oh yeah, I'd be interested in like hearing more about that use case. I think we can sort of discuss that in detail later.
Alfonso, I think you had a question.
Oh yeah, so thank you very much for the talk, Pradeep. It was very nice. I I feel very lucky to be presenting afterwards. Just to mention, because I think we all have seen how verbose can get this thing of having to specify the literals, like saying tensor of literal 2, literal 3, literal 4. I just wanted to make sure that we align on the vision that it would be nice if the user could just type like the exact dimensions as values and not as type like literal something.
Yeah, agree. And I think this also serves as documentation if we can make it more succinct and readable. So right now it's we have to specify multiply, stuff like that. If you could just, I see a lot of documentation that says, hey, the shape here is this, or this is the sort of, this is what we do. I think types could help just replace that manual, unchecked documentation.
Would that look like a tensor bracket? I saw in chat you're suggesting like add it like a tensor type and then just put dimensions in it directly.
Yeah, like that would be tensor bracket 2,3.
It would be interesting to support arithmetic as infix rather than as a type in just
Yeah,
within
I mean,
a tensor.
that
I don't
was
know
a quickly taken decision
messy,
for a well,
Oh,
fast
okay.
consensus, let's say, but yeah, not set on a stone, of course.
I think there's some discussion in chat about like NumPy differences, but I don't know if there's, I don't know if anyone has like something they want to raise verbally.
I think it was mostly just about the issue of how we would type an in-place transpose, but I think that's enough of an edge case that we don't need to talk about it in too much detail.
Yeah, perhaps also raises the topic of when NumPy or Python want to adopt types, should they modify their API or should we make everything as similar as what they support even? But we see that sometimes it's just impossible, no? But like the case of the transpose was an example.
Niels had a question.
Hi, Pradeep. Thanks so much for your presentation. My question is just about where would you recommend using, well, when this approach is more mature, like when would you recommend using this approach versus like property-based testing, writing unit tests for these kinds of, to catch these kinds of errors?
Yeah, I don't think we're at the sort of guidance stage where you can say this is better or the other. I think we're still trying to figure out what works best. Yeah, I think I'd mentioned that unit testing is rare, at least in the code I've looked at for machine learning projects, or it doesn't cover all the branches, for example. So if you have core parts of your library, those could be like well typed with shape types, and maybe other code could not. That could be one option. Matthew, did you have opinions?
Yeah, I guess the other thing to say on that is that a lot of machine learning code at the moment is written in the context of experimentation, where maybe writing unit tests isn't the right thing just because your code is changing so fast that you waste a lot of time by writing unit tests. So part of the vision here is just like give people an easy way of catching errors than unit tests. But for code which, yeah, like Pradeep said, for code which like is core and which has been nailed down, then yeah, still write unit tests. The other thing, I guess the other thing is that unit tests aren't documentation, whereas one of the nice things about the annotations approach is that you then annotate your code directly with the expected shape. Part of the reason I got excited about this was trawling through so many code bases where a function just says takes a tensor, and I'm like, I have no idea what that's supposed to be. So yeah, the other benefit, I would say it's not a sort of first tier is annotation and then second tier is unit testing. It's like even if you have unit testing, it's still really nice to have these annotations.
And Guido had a point.
Yeah, I noticed that once you start using things like literal 2 and literal 3, everything gets very verbose. Have you considered just proposing some kind of shortcut where if you use an integer in a type, it just sort of automatically means the corresponding literal type?
Yeah, we would love something like that, because I think we had a lot of trouble just writing literal everywhere. So I think we were just concerned about upstream changes. But yeah, I think that would be a great addition to the literal type arithmetic PEP when it comes out.
Yeah, well, that's not going to happen sort of if you don't push for it.
Yeah, makes sense.
Okay.
Stephen?
Yeah, I just wanted to say with regard to the unit testing, I think in addition to like correctness and catching bugs, a big thing that I would have found this useful when I was doing scientific computing is more the hover. Like it's one thing to have documentation on a function. It's another thing to be threading variables through code that's implementing some paper and to try to keep track of the shape of every tensor. And I think that kind of IDE support would be hard to get through some other mechanism as well as you could through type support.
I think that definitely makes sense. We showed it to some users and they were, yeah, similarly, they felt similarly about it.
We're at about time, so we can maybe, if no one has any lingering questions or comments, we could switch to Alfonso's, which is about a very similar piece of this. So.
Sure. So thank you very much. And of course you can go to the breakout room, but I think it would be very interesting if you could stay for the talk, since I think it's very connected. So yeah, let me share my screen. 1 second. Can you confirm that you are seeing everything fine?
Yeah.
Yeah.
Yep.
Okay, 1 second. Okay, so thank you very much for attending the presentation. For those of you who don't know me, I'm Alfonso, and I'm going to talk about a proposal that I made a few months ago about how to bring type arithmetic to Python and use it for tensor typing. I feel very lucky that Pradeep and Matthew had this talk right before me, because I think that they have explained very well the motivation behind this, the importance that it plays, the pain points, and I do hope that this will allow you to understand better what I will talk about. Nonetheless, I will try not to focus too much on selling this proposal, because that's not the goal, but rather on trying to gather feedback to make sure that we are aligned, that we think that this is what we want, and to make sure that if this will go for a paper route, or rather like to discourage it, right? So yeah, as you have seen right now, like we are in a very good situation with tensor typing, because the latest work on variadics has enabled a lot of things, and we start to face, well, to be able to type a lot of different libraries, different frameworks, and overall very useful. What is unfortunately the sad truth? The sad truth is that when you start using just a single function that makes a transformation on a dimension, you automatically lose the information about what that dimension is, because you very easily will do something like a concatenation. You will say, okay, I have two tensors, size A, size B, I concatenate, now it's A plus B. And now if you cannot express that, basically you cannot tell what number goes after, right? And this appears in very simple transformations, right? Can be an addition, a multiplication, a division, subtraction, like this appears all over the place. And if we cannot model this, we won't be able to take advantage of the dimension that we are specifying in the rest of the code. And with the same building blocks, we can express even more complex things, right? In the case of convolution, Pradeep showed like the picture of the formula. This is how it will be typed. And basically, at the end of the day, this is just plain arithmetic, right? I mean, it's true, it's a complex expression, but it's just arithmetic. And in the case of complex transformations, I think that it's not just very interesting because it allows you to check that the shapes are correct. But obviously, that's very interesting. But the other point I think that plays a very important role is to help the programmer to infer what are the dimensions, because there is a very requested feature in PyTorch, for example, that is I'm writing some layers and eventually I lost track of what the tensor looks like because I have done a lot of transformations. Well, you have seen that you could just hover on top of the mouse, say the return type that is inferred, and you would already know what's going on. You wouldn't need pencil and paper and do the calculations by your own. And also, I want to highlight that this is not just for pure machine learning. Overall, this can be applied to anything that uses fixed size containers. For example, let's say that we have a list of a given size. We can model the concept of appending an element to a list, or even getting a slice within a list. We can also model it, right? So this is an example of how, even if for some reason this wouldn't get within machine learning, it still opens the door for interesting applications outside of that topic. And overall, I think that this is fundamented in a very basic concept that is making arithmetic on integer literals. Because nowadays we can have two variables like literal 2, literal 3, but when we make, let's say, the product, it won't be literal 6, it will be an integer. And this is, well, this is very sad, because this would enable us to have all what I had just shown, because if you move this to the symbolic case where you have type variable, then if you make the multiplication of x multiplied by y, what you will have is the exact multiplication of x multiplied by y. And this is valuable because this can be even the input that you will give to the tensor after, right? So it's not the same to tell, okay, this is a tensor of any dimension, that is a tensor of the width multiplied by the height. Like, this is telling you a lot more information and letting you track all this. At the same time, I want also to, throw some cold water on the proposal and make sure that this is not something magical, like this is not going to solve all the problems, and what type arithmetic is not. So here we are not trying to introduce any sort of advanced dependent typing. I know that this might look very interesting, but this is not part of the proposal. We are not trying to make some kind of refinement types where you make sure that you validate the elements that you're taking from a list. And this is orthogonal to constant expressions or const generics in C++ or Rahtz, because this is not connected at all with the runtime value. This is all in the type system. So like, that's orthogonal. So at this point, I think that I can summarize what is the main goal of the proposal in type arithmetic. That is, okay, let's focus in a few basic operators, namely addition, subtraction, multiplication, and division, and build support inside the type checker. Let's the type checker understand fully how they work, so that when the user wants to use them, they won't need any additional effort, any overhead. It should be as natural as possible. And at this point, you may wonder, okay, like, we may agree in this goal, but why these operators? Like, why not more? Why not less? Where is the limit, right? So the thing is that there is a very important point that I haven't mentioned yet, and that thing is equality. Equality is not that kind of thing that comes to your mind the first time, but in the moment that you start writing code, it appears all over the place. How does it appear? Well, something so simple like you make a concatenation of two tensors, A and B, and then you make it again opposite order, B and A. Obviously, they have the same size. One is A plus B, another B plus A. However, for the type checker, this is far from trivial. They are different expressions. This can happen, again, you add and then remove an element. You have +1 minus 1 is equal to 0. I don't know. Like, all the things that for us are trivial, for the type checker, they are not. So how do we solve this? Because without this, it's pretty much useless. Because in the moment that you face one of these situations, how do you solve it? The few languages that have such a concept of type arithmetic, they will tell you, okay, A plus B is equal to A plus A. Provide a proof. You have some theorem proving in the language, it will ask you, okay, prove it. But I think that we all agree that Python is not going for that route. We want to keep it as simple as possible to make it simple for the user. So here is where we want to take advantage that we are limiting ourselves to a few operators to make sure that we put the effort on the type checker side to make sure that for the users it's as simple as possible. And I don't want to get too much into detail because of time and because I commented in my previous talk in case that you have seen it. But the key idea is that we can build a canonical representation that guarantees that if we take two expressions that are equivalent, when we normalize them to this representation, they will look the same. And by doing so, basically, we add zero complexity to the user because are the type checkers who are responsible for this. This way, there is no theorem proving involved, nothing like that. It's just something that is possible because these basic operators can be normalized into this. Here, there is only one remark in the case of division, because division is a bit trickier to normalize. And the way we went when I work on this in Pyre is that we realized that most of the time, we don't have super complex expressions. So we decided to go for a route that is, okay, let's do something that is fast, that works 95% of the time. And in exchange, instead of going for a route that is, okay, 100% equality, but you need to implement almost a computer algebra library inside the type checker. So we made that compromise. Nonetheless, this is not set on a stone, but it's the kind of thing that, well, you need to decide when you're working on this. And so far, you have seen the examples with convolutions, things like that. So far, you don't face cases where this is not powerful enough, right? With this, I hope that I have showed you the very important role that the quality plays and that perhaps prevents other languages from supporting type arithmetic, because this is not a trivial problem to solve. There is another design decision that is important, and so far I have intentionally not mentioned it, and is, okay, what is the domain of type arithmetic? And what do I mean with the domain? I mean, okay, now let's define our tensor class. I will need to put there a type variable or a variable. What do I put there? So far we have said that arithmetic is all literals, no? So maybe the thing that will come to your mind is, okay, we want to say that it can only be a literal end, but how do we say that? We can't really do that. So let's suppose that we introduce a new type variable in the language that is called int variable. That sounds like very appropriate, and is the union of all the literals. Okay, so far so good, but the thing is that very often you have dimensions that you don't know. Like something so typical as you're reading a CSV file, you know the number of columns, but you don't know the number of rows. What would you write there? Perhaps an if approach would be, okay, I write here type variable A, like trying to say that I don't really know it, but I know that it's valid, so I would like to drag it somehow. But obviously this wouldn't work because it would be an unbound variable, and probably it wouldn't be doing what you expect. So maybe after this, you think a little more about it and you say, well, actually what I want is a type that is the union of all the literals, let's say that is any number, and my type variable is bound by that. So now I can go and write any number. But so far, we have found ourselves introducing a totally new concept in the language that we will need to define how this interacts with other literals. Addition of this plus any number, like what would it be? What the addition with it? How would this play with the rest of the language? And instead, what do we need? What we need is something that is unbound, that represents every possible literal, and one thing else that should be a super type that should represent the unknown. But we already have something like that, right? And that thing is called int. We can do something so simple, perhaps less fancy, but very practical and very capable. That is to say, okay, this is bounded to int. What does this mean? That you can provide any literal, and when you don't know what is it, you write int. And int, what does it represent? It represents the unknown. It's a number, but I don't know which. And if you have a number that you don't know which is it, and you add a number to it, what is the result? Another number that you don't know, right? So we can encode this in the arithmetic, and we can say int plus anything is int, int multiplied by anything is int, and so on and so forth. So with this, without being very ambitious, rewriting a lot of parts of the type system, we can get a type arithmetic very easily integrated. And well, this is the second key point, the decision that I wanted to highlight, because it's worth discussing. This is again not set on a stone, and maybe you have other experiences about how to approach this problem. But yeah, it's not that we haven't thought about other approaches, but we tried to do, and then we saw that there are simpler and perhaps better ways. And because I want to keep this discussion focused, I don't want to extend too much, but if you have attended the previous presentation, you may know that there are other operators that I was proposing. The thing is that because we haven't yet agreed that we want this feature and we want it soon, let's say, I didn't want to put the emphasis on how powerful this can get. I want us first to agree, okay, do we think that the core idea makes sense? And if so, to extend it. But nonetheless, I thought that it still can be interesting to mention them and discuss them. So for example, from my experience, I realized that there are times where you need to do something a bit different, but that still is producing numbers. Like, okay, I want to make the product of all the dimensions of a tensor, like, because in this case, the product of a variable that takes a variable and returns a number. Another example would be if you want to get the length of a variable, like how many dimensions does a tensor have? How many elements does a tuple have, right? So this appears in actual functions. And I think that this is, in the case of length, a good example of how type arithmetic can get related with other aspects of the language. Because right now there is an open problem with variables. That is, okay, how do we constrain the length of a variable? Right now, you can't really constrain it. And in some very common functions, in NumPy, for example, you may need to remove the k element of the variable, right? The k dimension. So actually with length, we could, I'm not saying that this is the way to go, I'm just saying that this would open the door to do something like the following. You could say that one parameter corresponds to the length of the variable. And by doing so, when that periodic appears later on in the code, the type checker should enforce that the length that you provided, in this case in access, is the same as the length of the variable when it appears later on. Obviously, this has advantage, disadvantage, but I think that it's a good way of saying how something like arithmetic can appear in other parts, or in general, something that produces a number and can be connected with other features. And if we want to be ambitious and to think even further, like, okay, we assume that we want this, we want to go even further, well, we can even think about including broadcasting. This is, well, all this that I mentioned so far was implemented and prototyped in Pyre, and so that it works. And in the case of broadcasting, it's very interesting because we can take two variables or two lists of dimensions and broadcast them at compile time. And I think that we all know that this is very important because all the big libraries like NumPy, PyTorch, TensorFlow, they have some concept of broadcasting. So it's not that super corner case. And it would really open up the doors because so far there are a lot of operators that in the case of broadcasting we can't model, and this would open the door for that. So, I mean, definitely something to be excited about, but again, we need the basic stuff first. So yeah, at this point, I just want to make a quick recap of what are the key ideas that can be discussed here. That is, first of all, like, do we agree that this is an actual problem? Do we agree that there are use cases? I mean, I do believe that the previous presentation has shed light on this, but I mean, we need to be sure about it. Then is the way to go to limit ourselves to a few operators and offer very good support for them? Or maybe we want something very general that maybe would add some complexity to the user, but that, let's say, would be more extensible, less, hard coded. Then even if we want to go that route, is this automatic equality checking the way to go? Are there alternatives? How, let's say, could be solved otherwise? Could it be even solved after all? And then is this basic idea of using index the known a good approach? Maybe I have discarded too easily the concept of all the literals. Maybe it does have side effects that we are not aware of. And then, well, is this proposal extensible in the sense that if we go for this route and then in the future we change our mind and say, no, we want something general, we want another thing, like, does this leave the door open for going in that route? So yeah, that's pretty much what I wanted to cover here today. And at this point, just let me mention that, I mean, I hope that with this talk, regardless of if you agree or you don't agree with the proposal, at least it has shown that it's possible to make type arithmetic in a way that is simple and powerful at the same time, that we don't need to have a super complex language to provide this feature and make it as simple and yet powerful to use for the user. So thank you very much, and well, looking forward for the discussion.
Matthew.
Thanks for the great talk, Alfonso. On the subject of whether this is going to be sort of something worth pushing forward, I think the biggest hesitation I still have is whether it's compatible with the view that labels within tensor variadic should refer to actual numbers or should refer to semantic types. For example, if we have like tensor square brackets a, should that symbol a map to like a number or a literal like 2? Or should it mean, if instead of a it was something like height, should that just mean, hey, this part of the tensor's shape is like a height-like type? Because yeah, so if we decide that height, let's say, does refer to a specific value, then obviously this works great. But if it just means sort of a semantic type, what does it mean to do arithmetic on semantic types? What's your current thought on that?
Well, first of all, it's a very good point, Matthew. Thank you for raising this topic. And I think that you raised it because you have tried both approaches and realized what are the problems that they have. And the thing, first of all, that we say is that right now there is no perfect solution. It's true that arithmetic is in some sense more powerful because it allows you to catch exact shape mismatches, not only semantics of you're trying to use an image or a video, but it allows you the exact dimension to infer things. So in the case of, I think that here the question is a bit about how far will we be able to go with the integration with other frameworks, if they would really be able to fully adapt their model to the type system. And I wish I had an answer for this, but I feel that only actually the people who are working on NumPy, PyTorch, TensorFlow will feel more prepared for this. But I do see the point also, say, this is a tensor where the first element is a batch and the second is the number of something. But that unfortunately also had problems because I do remember very well trying with this, and then you have problems of what is a subtype of what because of covariance, and you want something to be accepted, and unfortunately, like none of them is perfect. So yeah, I do have the same question, and I don't have an answer for this yet.
Yeah, I suspect it will just be something that sort of we have to figure out empirically. Although on the point of sort of waiting for the library authors to do it, I think a pretty important thing for my philosophy in this is like we shouldn't even necessarily assume that the solution Pradeep and I outlined in the last talk is the right solution, and we therefore shouldn't start suggesting to library authors to adapt this before we've done some more experimentation ourselves. And I think what that would look like is, instead of suggesting to library authors to start writing stubs, we should start expanding, for example, the stuff that Pradeep has made on his GitHub of writing stubs ourselves that then can be used for people willing to experiment, rather than pushing the library authors themselves to do it.
Totally, I think that makes sense. Nonetheless, I feel that there is still some value. For example, in the case of the arithmetic, even if there wouldn't be machine learning involved at all, I think still doing some operations on literal can enable some use cases. But yeah. So the next is Ethan, perhaps.
Yeah. Hi. Yeah, I think type level arithmetic is very important, but also very complicated part of a type system, especially once you get like periodics. So I guess my question was about equality checking, because that is such a central part of type level arithmetic. So you said that you were not as excited about full quality checking. I think you said that you took a simplified approach to it.
In the case of division.
Yeah. Just in the case of division.
Yeah.
Okay. I see. Okay. Yeah. Because my understanding is that like if you relax the equality checks, then that causes problems.
Yeah, totally. Because there is no alternative. If it doesn't type check, you cannot do it differently. You could force a cast or something, but yeah, I mean, in the case of division, maybe I can give a little more context, but well, as you saw, I think in the example, there are some very complicated simplifications, and often it's enough to make like take the common monomials that appear, make the greatest common divisor, rather than having a more advanced computer algebra thing that maybe a scientific SciPy can provide, right? But that maybe because we didn't see an example where that complicated case was happening. And I think that it also opens a meta question, that is, if in the future we will want to expand to other operators, how important is that we enforce equality in those operators? There could be a world where some operators are fully enforcing the quality and others are not. Could that be possible? Maybe some operator, they don't have so many properties. Maybe when you are doing a power is not commutative, or is not distributive, or something like that. So yeah, that's a meta question.
Thanks.
So Guido.
Muted.
Couldn't find my mouse. So my meta question is, what do the developers of say NumPy, Pandas, TensorFlow, PyTorch, other packages in that space think of this. I'm not even a user of those packages, so to me, it's all like totally abstract math. But sort of we've received feedback from the steering council in the past that we need to make sure that when we claim a certain feature benefits a certain subcommunity, that we actually talk to the users and the core developers in that subcommunity. So how much of that have you all done here?
Definitely a very relevant question. It has also been my aim to clarify this question, and I think that was one of the reasons why we started to organize the Tensor typing monthly meetings. So also the reason perhaps why we were interested in the summit. In general, to attract people that they are not so up to date with TypingSig to answer these questions. And in the case of NumPy, I'm afraid that I don't have an answer, but I feel that, for example, in the case of frameworks like PyTorch or TensorFlow, we may have further support because, well, when we were working on this feature at Facebook, I felt that from the PyTorch side that there was sense on this, and I guess that from there they can get more quick interaction in the case, for example, Pradeep or so many people here that are working at Facebook. And in the case of TensorFlow, I don't have that much experience or on JAX, so I couldn't really say, but well, maybe Matthew has a little bit more context on that. But I think that, yeah, everyone is looking for something that can make life a bit easier, maybe not the perfect solution, but maybe it is a bit better, would already be helpful. Maybe Matthew?
Yeah, to expand on what Alfonso said, I've had some like pretty positive inclinations from folks working on NumPy and also the new Google machine learning framework called JAX. I've tried a couple of times to reach out to TensorFlow and PyTorch folks on their public mailing lists, but haven't got much reply to my 2 posts so far. One was a request for comment on PEP 646, and one was an invitation to join this meeting. So I think the next steps on that, we're going to have to be to reach out to particular people in those communities. But yeah, so the quick summary is like JAX and NumPy, the impression seems to be very positive and something that we have at least one core developer saying would be super good. TensorFlow and PyTorch, we don't have any communication channel set up yet.
Yeah,
you should really sort of try to reach out through internal channels if you have them.
Yeah,
yes.
so I think I can share that sort of we're right now focusing on getting, say, a small repo working correctly for end to end with shape types, and then like use that as a sort of showcase of what shape types can do and what they can't do. So that we're using that as the sort of current code. So once we have something working with, say, working for a small project, we plan to sort of just use that to communicate with library authors.
But
Can I make us
library authors what their pain points are, right?
Yeah.
I would make a suggestion if any of you are attending SciPy that you do a lightning talk on this, because I think you will get feedback if you do that.
That's a super nice idea, Carol. When is that? Do you happen to know off the top of your head?
Sometime in July.
Awesome. We'll check that out. Thank you.
You're welcome.
I think Brandon's been waiting for a bit, but do we want to move to so I'm going to paste a link in the chat that we can move to maybe after, where we can continue to chat either about this or other things. It kind of helps with like simultaneous discussions. But yeah, maybe Brandon, go ahead.
Just to mention, I haven't really had time to check the chat in order, so if I have skipped some questions, like raise the hand. So yeah, Brandon.
Oh yeah, well, if we're pressed for time, I can maybe ping you in another channel. But I think it's a great idea. As speaking a little bit towards the usability aspects, I know a lot of stage DDSLs implement something like this at runtime, and whether it's worthwhile pushing into the language is kind of another set of questions. But it seems like a lot of people kind of reinvent the wheel, so maybe it's a useful thing. Another thing that might be interesting to see is like, probably a little still early in the development, but what is the latency for tools to predict for certain workloads like you typically see in machine learning? You know, what is the time it takes to check these, and if it's beneficial to do this instantly, you know, or you can do this, you can wait till later. So, but yeah, thanks again. It's a good presentation.
Thank you, Brandon. Yeah, actually, what you said about the interactivity and so on is true that it would depend on the type checker. I don't know. Maybe those type checkers that are more incremental, they can offer instant responses. But I think that indeed this will help to unify a bit some effort that now are spread, because I think that there are like many attempts to do similar things, and even I think in PyCharm they have their own language server for making their own inference, and probably they implement their own mechanics. So having the thing specified in the PEP and you know, in a common place that doesn't need to be reinvented, I think that is one strong point. So thank you very much for raising it.
All right, awesome. Thanks everyone for a really interesting typing summit. So I think that's all of our presentation topics.